In this video, I'm going to cover chapter 5 of my stochastic modeling book about martingale theory, including the optional stopping theorem, the upcrossing inequality, and the martingale convergence theorem. I'm also going to give you additional results about the convergence theory for martingales, and we are going to apply all those results at the end of this video to get a complete proof of the strong law of large number, even in the general case when dealing with random variables that may have an infinite variance. So this picture shows you more precisely the different topics we are going to cover along with their logical connections. As usual, if you are interested in a specific topic, check out the thumbnail of this video or the description of the video with the different topics we are going to cover and the specific timings, so you can directly jump to the part you are interested in. The concept of martingale was introduced by mathematician Paul Lévy, but most of the earlier results about martingale theory were proved by mathematician Joseph Doob. Here are again the topics we are going to cover with the logical connections. So first, I'm going to remind you the definition of martingale, submartingale, supermartingale. I already did that in the previous video that covered chapter 4 of my book. I'm going to remind you this definition. I'm also going to define the notion of stopping time with respect to a sigma algebra and the notion of a process stopped at a stopping time t. So putting together the notion of martingale, submartingale, supermartingale with this notion of stopping time gives us the first main result about martingale theory called the optional stopping theorem. So if you think of a martingale as a model for a fair game, the optional stopping theorem tells you more or less that you cannot beat a fair game, in the sense that no matter what is your stopping time, so which means more or less no matter the strategy you are going to follow, as long as your decision to stop playing is based on the information available, the information you know, like the past including the present, you cannot increase on average the amount of money you have. Okay, so yeah, one way to summarize the theorem is to say you cannot beat a fair game. It turns out that obviously the optional stopping theorem is not something that we apply only in the context of games. You have martingales that are used in physics, biology, sociology, and so on. And in all those contexts, the optional stopping theorem is a very powerful tool that can be used to compute probabilities of events or expected values of random variables using a minimal calculation. It's a very elegant technique, but of course you would have to find a martingale in the background to be able to apply this theorem. So this theorem is probably the most useful of all the theory of martingale when you deal with martingales in practice. Another application of the optional stopping theorem, more on the theoretical side, is this upcrossing inequality here. That's the second thing we are going to do. We are going to prove that using the optional stopping theorem, we can prove this upcrossing inequality. So the upcrossing inequality says more or less that if you have a super martingale, let's say, and an interval AB, then you can define the number of upcrossing of this super martingale as the number of times your process is going to go from below A to above B. So number of times the process is going to cross the interval going up. Okay? And the upcrossing inequality gives you a bound for the probability that the number of upcrossing is going to be larger than some fixed integer. Alright, so this upcrossing inequality, contrary to the optional stopping theorem, is not useful in practice. We don't typically use that. That's more a very technical result that is used to prove the next main result, the second main result about martingale theory, which is called the martingale convergence theorem. Alright, so the martingale convergence theorem is, I would say, the first result, the first main result about the convergence of martingales. And this theorem tells you that if you have, again, can be a martingale, but also some martingale, super martingale, bonded in L1, okay, uniformly bonded in L1, then the process is also going to converge almost surely. So that's a very strong result in the sense that typically for a stochastic process, the best we can expect, and we'll see that when we deal with Markov chain, the best we can expect is convergence in distribution. If you go back to chapter 3, you will see that convergence in distribution is the weakest type of convergence we saw, while convergence almost surely, it's a very strong type of convergence. So typically when you have a stochastic process, you expect the process to show some, like to display some random fluctuation, but it's not the case if you deal with a martingale that is bonded in L1. In this case, you have convergence almost surely, which means that for almost all realizations of the process, eventually your sample path is going to converge to a limit, and you do not see those random fluctuations. Okay, so of course the limit of your sample path may depend on the realization. So you don't have convergence almost surely to a fixed value, like in the strong law of large number, for instance, but still you have convergence to a value that depends on the realization. It's still a strong result that shows that for a martingale bonded in L1, you do not see those random fluctuations that just keep on going. Eventually you have convergence to a fixed value. Alright, so eventually convergence almost surely to a random variable. So these are the two main results, I would say. You have many more results that cover what I want to call the convergence theory for martingales. And all those results are summarized here, okay, at the bottom of this slide. So I'm not going to prove all the implications, I'm going to prove only some of them, but let's go through that quickly so that you know what's going on. So the first important aspect about the convergence theory for martingales is the fact that if your process converges in LP for p strictly larger than 1, then it's going to converge to L1, okay, which itself implies convergence almost surely. Alright, so those two implications, we kind of already know them, we can just prove them right now. The fact that convergence in LP for p larger than 1 implies convergence in L1, it's something that I proved already when we covered chapter 3 about the convergence of sequences of random variables. That's a consequence of Jensen's inequality that tells you that the LP norm is less than the L1 norm for all p larger than 1. So this implication is not true only for martingales, it's true for any sequences of random variables. Now, the fact that convergence in L1 implies convergence almost surely is an easy consequence of the martingale convergence theorem. If your process converges in L1, then of course it should be bonded in L1, and by the martingale convergence theorem, you have also convergence almost surely. Now, remember that in chapter 3, I gave you an example of a sequence of random variables that converges in L1, but not almost surely. So that shows that this implication here, convergence in L1 implies convergence almost surely, is not true in general, but it's true in the context of martingales. Okay, so you have this first aspect here. Another interesting aspect of the convergence theory for martingales is the fact that if your process is bonded in LP for some p strictly larger than 1, then the process is also going to converge in LP. That's a very strong result. Bonded in LP, a priori, is much weaker than convergence in LP. In the context of martingales, the two are in fact equivalent. Okay? Notice also an interesting aspect of martingale theory is the fact that here I'm taking p strictly larger than 1, but you do not have any connection between bonded in L1 and convergence in L1. It's possible for a martingale to be bonded in L1, but this martingale is not going to converge in L1. but if the process is bounded in LP, then you have convergence in LP if P is strictly larger than 1. So this result here, this implication, is true when P is strictly larger than 1, but not if P equals 1. So that tells you that among all those LP spaces, the case of the L1 space is a special case. Okay? So that's some kind of summary of the convergence theory. Then after you see different concepts here also. You see that if you have, I'm going to define this notion, a martingale, then this process is a regular martingale. If and only if it is uniformly integrable. If and only if it converges in L1. So those three notions, regular martingale, uniform integrability, and convergence in L1, for martingales, those three notions are equivalent. Okay? That's another thing. And then, last result that is important is the fact that a reverse martingale is a particular case of regular martingale. So again, I'm going to define all those notions. Maybe briefly, I want to quickly tell you about reverse martingales. When you define a stochastic process, typically your filtration goes from time 0 to time plus infinity. And so your limiting sigma algebra is the one at plus infinity, that's the largest one. For a reverse martingale, and some people call that a backward martingale, because you can think of the process as a martingale that evolves backward in time. In this case, in fact, your sequence of sigma algebras that represents your filtration, instead of going from time 0 to time plus infinity, they start from time negative infinity and they stop at time 0. Which means that your limiting sigma algebra is not the one at plus infinity and is the largest one. Your limiting sigma algebra, that's the one at negative infinity, that is in fact the smallest one. And using those aspects, you can prove that this process, such a process called reverse martingale, is a regular martingale. And so you have also uniform integrability and convergence in L1, and then convergence almost surely. All right, so I just gave you like a summary of an explanation of all those arrows here. All those arrows here, they mean implication. You see that some of them are dashed arrows, some of them are solid arrows. The difference is that the dashed arrows, I'm not going to prove them, okay? I'm only going to prove the solid arrows. Covering all that would be too long, and so I decided to only give you the result that we need to eventually get a complete proof of the strong law of large number. Okay? So after proving the martingale convergence theorem, the next thing we are going to do is prove that if a martingale is uniformly integrable, then it converges in L1 and almost surely. Okay? Then after, I'm going to prove that if a martingale is regular, then it is uniformly integrable. And then I'm going to prove that if a martingale is a reverse martingale, then it must be a regular martingale. All right. And so combining all that, we'll eventually obtain that following this path of solid arrows here, we'll have that if you have a reverse martingale, then this process is going to converge almost surely. The theorem I'm going to prove is also going to give you some kind of implicit expression of the limit in terms of conditional expectation given like the limiting sigma algebra in your filtration. And so the fact that a reverse martingale must converge almost surely, okay, following this path of implication, is going to be a key to proving at the end of this video the strong law of large number. So that's going to more or less cover everything I'm going to do about the theory of the convergence theory for martingales. Then to prove the strong law of large number, we'll need one more result that is interesting in itself. That's Kolmogorov 0-1 law. And this one can be proved using the martingale convergence theorem. So after covering all the theory of martingale, I'm going to give you applications of that. The first application that is going to be useful to get the strong law of large number is called Kolmogorov 0-1 law. The result is not only interesting to prove the strong law of large number, that's a result that is interesting in itself, that says more or less that if you have a sequence of independent random variables, and if you have an event, let's say A, that is called a tail event, so a tail event is going to be basically an event that only depends on the tail of your sequence, meaning that whether this event occurs or not is not going to change if you change the outcome of only a finite number of those random variables in your sequence. So if you have such an event, then this event must have probability 0 or 1. Okay? You are in one of those two extreme cases. This result has some similarities with the two Borel-Cantelli lemmas we saw in chapter 3. In chapter 3, we saw that if you have a sequence of events, then the lim sup of this sequence, which is the event that infinitely many of your events are going to occur, is a new event that must have probability 0 or 1 under the condition that you have independence. This result is very similar to the two Borel-Cantelli lemmas, but in some sense a little bit stronger, because instead of dealing with just the lim sup, it deals with any possible tail event that depends on the tail of your sequence. All right, so that's going to be the first application. Then combining the fact that a reverse martingale converges almost surely and Kolmogorov 0-1 law, will be able to prove the strong law of large number. The idea will be to find in the background of the strong law of large number a reverse martingale, then we'll have convergence almost surely, and we can identify the limit using Kolmogorov 0-1 law. And so to conclude this video, I'm going to combine those two results to finally get a complete proof of the strong law of large numbers. So I already gave you a proof of the strong law of large numbers, which is one of the most popular results in probability theory, when we covered chapter 3 of my book. The proof was based on an application of Chebyshev's inequality and the first Borel-Cantelli lemma, but Chebyshev's inequality needs to have random variables that have a finite variance. While combining those two results, we can in fact get a complete proof of the strong law of large number that is more theoretical and that gives you also the results when dealing with random variables that may have an infinite variance. So first, let's look at the optional stopping theorem. So I need to start with a few definitions so that I can state the theorem. So first, we said that the process Xn is a super martingale with respect to Gn. So Gn is a filtration, meaning that in the background you have this probability space omega Fp. Gn is a sequence of sub-sigma algebras of F, and this sequence is non-decreasing. Okay, so that represents your knowledge at term n. That's things that I defined in the previous video covering chapter 4. So we said that the process Xn is a super martingale for this filtration Gn if all the Xn are integrable and your stochastic process is adapted to Gn, which means that for all n, Xn is Gn measurable, or also if you know Gn, then you know Xn. Okay? The second condition in blue here, that's the main one, the one we use to prove theorems, tells you that the conditional expectation of Xn plus 1 given Gn is less or equal to Xn. All right. So remember that it helps, even if it's not always the case in practice, it helps to think of Xn as the fortune of a gambler playing an unfavorable game. And n, time n would mean the fortune after playing n games. Alright? So this condition basically tells you that no matter what happened in the past, including the present, represented by Gn, on average, the amount of money you are going to have at the next time step after playing the game one more time is going to be less than the amount of money you have right now. All right, so that's the definition of super martingale. I'm going to stick to super martingale for a little bit. The reason for that is because it's more general than looking at just martingales. If you have a sub-martingale, then it's easy to see that if xn is a sub-martingale, then minus xn is a super-martingale. And so everything I'm going to prove is still true for sub-martingale. You would just have to switch all the inequalities. And because a martingale is a particular case of a process that is both a super-martingale and a sub-martingale, everything I'm going to prove is again true for martingales, but instead of inequalities, you have equations. Okay, that's why I'm looking at just super martingale. That's more general. All right, so first observation about the process is the fact that if you take the expected value here on both sides, okay, remember from chapter 2 that the expected value of the conditional expectation here is just the unconditional expectation. So the expected value of this random variable is going to be just xn plus 1. But because the expected value is a monotone operator, from this inequality, you can easily deduce that expected value of xn plus 1 is less than the expected value of xn. So taking the expected value in 2 tells you that if you have a super martingale, the sequence of expected values is non-increasing. Okay? The proof is just here. That's very easy. So from the definition, you can say that the expected value of xn is equal to expected value of the conditional expectation of xn given gn minus 1. Here I'm using just a basic result that we proved in chapter 2. Okay? Then from the definition, you see that this conditional expectation here is just xn minus 1. And so that tells you that expected value of xn is less or equal than expected value of xn minus 1. If you keep going by induction, you can prove that the expected value of xn is less than the expected value of x0. Okay? If you have a sub-martingale, the inequalities are reversed, so you have that the expected value of xn is larger than the expected value of x0. Okay? So the sequence of expected values is non-decreasing this time. If you have a martingale, the sequence of expected values is going to be constant. All right. So have in mind that martingale implies sequence of expected value is constant, but the converse is not true. You have stochastic processes such that the sequence of expected values is constant, but still the process is not a martingale. We saw a counterexample in the previous video covering chapter 4 that was this sequence of coin flips. You flip a fair coin, you assume that xn is equal to plus or minus 1 depending on whether you get heads or tails. This defines a stochastic process. You assume that those xn are independent. We prove that in this case, expected value of xn is equal to 0 for all n. So the sequence of expected values is constant, but we also prove that xn is not a martingale or a sub-martingale or a super-martingale. Okay? So first result we have here is if you have a sub-martingale, super-martingale, or martingale, the sequence of expected values is monotone, at least, or constant in the case of martingale, but the converse is not true. All right. So this first step is kind of to motivate the optional stopping theorem. So you see that if you have a super martingale, expected value of xn is less than the expected value of x0. If you go back to the context of games, in this case you have an unfavorable game, that would mean that doesn't matter when you stop playing, okay, if you decide to stop playing at some fixed time, then the amount of money you have at the end on average is less than the amount of money you started with. Now, the question is it true Okay, is this result still true if I replace this time n, deterministic time n, by a more general random time? Okay, that's the main motivation behind the optional stopping theorem. Can we replace in this inequality n by a random time, let's say capital T? Okay. And obviously, let's say that we go back to the context of martingales in which this is equal to that. This would tell you that if you play a fair game and you decide to stop playing at some fixed deterministic time, then on average, you did not win anything. The question is, well, now if you can make this time random and you decide to stop playing at some specific random time that kind of depend on your knowledge, can you do so that the expected value of xt, if t is your stopping time, is your random time, can you make this quantity larger than x0, expected value of x0? All right, so the answer is yes, this is still true, but not for any random time. You need to have what we call a stopping time, and I'm going to define this notion. Stopping time is, in fact, so the definition looks a little bit theoretical, but in fact that's something very, very natural in practice. You just said that t, I'm going to look at the interpretation first so that you understand the logic. We said that a random time t, okay, so that's basically a random variable but with values, integer values that represent a time, and you can think of it as the time at which you decide to stop playing the game. So t is going to be a stopping time if your decision to stop playing at time t cannot be based on the future. So t is a stopping time if basically your decision to stop playing at this time depends on what you know on past and present, and this decision cannot be based on the future because you don't know the future. Okay, so how do we write this mathematically? How can we go from this sentence in English to a mathematical definition? Well, the definition is here. The notion of stopping time, exactly like for a martingale, should be with respect to a filtration Gn. Okay, so a stopping time t with respect to a filtration Gn is going to be a random variable. So by random variable, we mean a function that is measurable and defined on omega. Okay, that's the same omega as here, your set in the background, with value in something that I'm going to call n bar. That's the set of all natural numbers, but I add to that infinity. Okay, infinity is a possible value for your stopping time. You may decide to never stop playing, in which case t is equal to infinity. So that's a random variable with values in the set of integers including plus infinity, such that, and this is the condition that tells you that your decision to stop playing should be based on past and present and not on the future. You need that for all n, the event that t equals n is in the sigma algebra Gn. Okay, and so this means exactly that your decision that you will stop playing at time n, if at time n you decide that you should stop playing, then this should be based on what you know so far, which is Gn, what you know from what happened in the past, including the present, but cannot be based on the future. Okay, so again, in practice, you cannot do better than that. Okay, so let's look at examples of stopping times so that you understand better this definition. I'm also going to give you an example of a random time that is not a stopping time, so that you understand also that not everything is a stopping time. Even if in practice we can only deal with stopping times because we cannot see the future, still in mathematics you can define random times that are not stopping time. So the main example of a stopping time would be what we call the heating time. Okay, so for instance, let's fix a Borel set B, okay, in your Borel sigma algebra, and then you can define time t as the first time your process xn is going to visit your Borel set B. This is a stopping time, okay? Intuitively, that must be a stopping time, because if you observe your process, you can say, well, I'm still not in B, I'm still not in B, and so on. And then you see that suddenly your process is in B, and you know at the time this happens, you know that it happened, okay? So this must be intuitively a stopping time. The way you prove that is by using basically all the stability conditions of a sigma algebra. If you look at the event for this specific stopping, for this specific random time, like the heating time, if you look at the event that t equals n, you can express that by saying this is the event that x1, x2, x3 up to xn minus 1 are not in B, but xn is in B, which you can write like this. Okay, that's the event x1 in B complement, intersection x2 in B complement, up to xn minus 1 in B complement, intersection xn in B. Okay, that's the way you can write this event, but using those xi. Now you see that because by definition x1 is f1 measurable, fn is going to be the natural filtration associated to the process, you see that this event is in f1, the second one is in f2, and this one is in fn. But a sigma algebra is stable by complement, so all those complements they are also in f1, f2, and so on. But all those sigma algebras are all sub-sigma algebras of Fn, which is the largest one, okay? But because they are all in Fn, but because, again, a sigma algebra is stable by intersection, the intersection of all these events is in Fn, okay? So you see that the event that t equals n eventually, because it can be written like that, is in Fn, but Fn is a sub-sigma algebra of Gn. Remember that we assume that xn is adapted to Gn, and remember also that the natural filtration, that's something I defined in the previous video, chapter 4, that Fn is the smallest filtration the process is adapted to. Okay, so that means that Fn is a sub-sigma algebra of Gn, so that shows that indeed the first time at which you visit a Borel set is going to be a stopping time that fits with our intuition. In general, you can prove that the second time, or the third time, or even like for any k, the kth time at which you are going to visit a Borel set is again a stopping time. Okay? Because to know that it's indeed the kth time this happened, you only need to know the past, including the present. Now, an example of random time t that would not be a stopping time would be the last time at which you visit the set B. To know that indeed time n is indeed the last time at which you visit the set B, you will need to know what's going to happen in the future. Okay? So that will make this event an event that is in F but not in Gn. Okay? And so the last time at which you visit a Borel set would be an example of random time that is not a stopping time. Alright, so now we have this notion of martingale, super martingale, sub martingale. The notion of stopping time. We are going to look now at super martingale stopped at a stopping time. Both should be with respect to the same filtration Gn. Okay? Then in this case, what you can prove is that if you have a super martingale, then the process stopped at a stopping time t is again a super martingale. That's the first main result that we need to eventually get a proof of the optional stopping time. So the thing is written here. You define the process xn exponent t. I'm using this exponent t to say the process stopped at time t. That's exactly the process at time the minimum of n and t. Okay? So you see that this quantity here is just equal to xn if n is less than t, but it's equal to xt if n is more than t, okay? And so, more or less, this process xnt is just the same as the process xn, except that in the background you have a stopping time. And you decide at time t, okay, you don't know exactly when it's going to be, that's a random time, but at time t you decide to stop your process. Then it turns out that if xn is a super martingale, then the process stopped at time t is again a super martingale. And the proof is here. So to prove this result, I just need to check this, but for the process stopped at time t, I can just inject the xn here, and I need to prove that the conditional expectation of the increment is negative, okay, or non-positive. So that's why I start with this quantity. Okay, I'm looking at the conditional expectation of xn plus 1t minus xnt given gn. We want to prove that this is less or equal to 0. Okay, so the way you do this is step 1, you can replace this expression here, this increment, by xn plus 1 minus xn times the indicator function on the event that t is larger than n. So why can we do that? Well, if t is less than n, less or equal to n, that means that your process was stopped before time n. And so if the process is stopped before time n, then those two random variables are equal. And so your increment here is just equal to 0. Okay? That's why I can ignore the set where t is less or equal to n. On this event, the increment is 0, so that's not going to change the conditional expectation to just multiply by this indicator function. That's basically the event on which this increment may be different from 0. Okay. Notice also that in this expression I just dropped the t's. Why? Well, because t is larger than n, and so because t is larger than n, at time n plus 1, we did not stop the process yet. So indeed, at this time t, those two random variables are indeed equal to those ones. Okay, just keep in mind that this one is either equal to xn or equal to xt, depending on whether t is more or less than n. So that's what I do here. I just get rid of what happens on t less than n because the increment is 0, but on this event, at the opposite, the increment is just equal to the increment of your super martingale in the background, like the process that is not stopped at time t, because the process has not been stopped yet. So that's the explanation for the first equation. Then, for the second equation, I'm using technique from chapter 2 about the conditional expectation. Here, I'm putting this indicator function outside the conditional expectation. Why can I do that? Well, according to what we saw in chapter 2, if you have the conditional expectation of a product of two random variables given a sigma algebra, if one of the two random variables is measurable with respect to the sigma algebra, then it can get out the conditional expectation. That's exactly what I'm doing here. I'm just using the fact that the event that is strictly larger than n is in Gn, which means that this indicator function here is Gn measurable. And so I can just put it outside the conditional expectation. That's the case of perfect information. If you know Gn, then you know this random variable, and so this random variable can go outside the conditional expectation. I proved that in chapter 2. Right, so just one little explanation that I need to give here is why is it true that t strictly larger than n is indeed in Gn, while the definition says that only t equals n is in Gn. But the event that t is larger than n is the complement of the event that t is less or equal to n. Okay? And the event that t is less or equal to n is the event that t equals 1 or t equals 2 or t equals 3 up to t equals n. And all those events are in Gn by this property, okay? Also because Gn is the largest of all the sub-sigma algebras among G1, G2 up to Gn, okay? And a sigma algebra again is stable by union, intersection, and so on. And so you can easily see from the definition here that the event that is strictly larger than n is in fact can be expressed as union, intersection, complement, and so on of events that are in Gn, and so this event is in Gn. So that shows that indeed this indicator function is Gn measurable, so that can get outside the expected value, the conditional expectation, according to what we saw, like a result that we saw in chapter 2. All right, and so now we are done, basically, because now you end up with a quantity, a conditional expectation that is the exact same as what we had at the beginning, except that the t's disappeared, and now they take the form of this indicator function in front of the conditional expectation. But now here we can use the fact that by assumption xn is a super martingale, okay, to say that the conditional increment here, by the definition here, should be less or equal to 0, okay? So this is less or equal to 0, but this indicator function is just equal to 0 or 1, so that means that the product is again less or equal to 0, okay? So that shows that the conditional expectation of this increment is less or equal to 0, so conclusion, the process stopped at time t is again a super martingale. That's the first tool we need to use to get a proof of the optional stopping theorem. So the optional stopping theorem is in the next slide, that basically says the same as this. If you have a super martingale, then expected value at some, not time n, but a stopping time t is going to be less than the expected value of x0. So more precisely, we have that. Assume that xn is a martingale. Assume that t is a stopping time, and that this martingale and stopping time are both with respect to the same filtration Gn. Okay? Then in this case, what we proved just before for a fixed time n is now true for the stopping time. So that means that expected value of xt is less or equal than the expected value of x0. So in each of the following two cases, you need extra assumption about the martingale and the stopping time. But before I give those assumptions, so let's look a little bit at this conclusion and let's see what it means. Let's assume that instead of a super martingale, we have a martingale. Then the result would tell you that expected value of xt is equal to the expected value of x0. And so that this result, that tells you that you cannot beat a fair game. Okay, if you think of your process as modeling your amount of money when you play a game, then this result for martingales would tell you you cannot beat a fair game. So if you have a fair game, then this process xn becomes a martingale, then you have an equation here. And so the theorem would tell you that it doesn't matter how you choose time t, as long as this is a stopping time, meaning that your decision to stop at time n is based on the past and the present and is not based on the future, because you don't know the future yet. So no matter how you choose your stopping time t, on average, the amount of money you have at time t is equal to the amount of money you have at time 0. Okay? So that says, again, you cannot beat a fair game. It doesn't matter which strategy you are going to use. You cannot, at the end, no matter how you choose to play, no matter when you decide to stop playing, at the end of the day, on average, you did not increase the amount of money you have. Okay? So this is not true always. For any super martingale or any stopping time, you need different conditions, so there are different versions of the theorem. I'm giving you the main two versions. So the first one says that the process xn stopped at time t must be bounded, and your stopping time t must be almost surely finite. Okay, that's one version of the theorem. Another version says that this is also true if the process stopped at time t has bounded increments and your stopping time is finite in expected value. Okay, so that's two of the versions. You have other ones. These are the two most common that we use in practice. So notice that none of the two implies the other one. Okay, having the assumption 1 is not stronger than 2, 2 is not stronger than 1. So why is that? Well, it's obvious that bounded implies bounded increments, but bounded increment does not imply bounded. Okay? Example of stochastic process that has bounded increment but that is not bounded is the symmetric random walk which we saw in chapter 4. That jumps right, left with the same probability 1/2. This process has obviously bounded increments. Okay, the jumps have length 1, but the process can go as far as you want to the right or as far as you want to the left. So that's an example of process that has bounded increment but is not bounded. But then at the opposite, there are random variables t that are almost surely finite. Okay, but if the tail does not go to 0 fast enough, then the expected value is infinite. Okay, so in 1, the assumption on the martingale is stronger than in 2, but in 2, the assumption on the stopping time is stronger than in 1. Okay, which means that 1 does not imply 2 and 2 does not imply 1, which means that both versions of the optional stopping theorem, none of the two versions of the optional stopping theorem implies the other one. In some cases, in practice, if you deal with a bounded process, then you want to use option 1. But if your process is not bounded, but you can prove that it has bounded increment before time t, then you want to check that indeed the expected value is finite, and so you want to apply the second version. All right, so now how can we prove the theorem? Well, the first key that we have to use to prove the theorem is the fact that the process xn stopped at time t is a super martingale, which is what we just proved. So using this, you can say the following: because your process stopped at time t is a super martingale, you can say the first thing here. You look at the limit when n goes to infinity of xnt, expected value of xnt. Then, because you have a super martingale, what we have is that this expected value here is less than the expected value at time 0. That's a direct consequence of the definition of martingale. That's what we proved just at the very beginning. So you have this, but then you end up with here a quantity that does not depend on n. So the limit when n goes to infinity, you can get rid of that. That gives you expected value of x0t. But the expected value of x0t is just the expected value of x0 because, well, even worst case scenario, you stop your process at time 0, still your original process is going to match with your stop process at time 0. Okay, so you get this limit when n goes to infinity of x and t is less or equal to the expected value of x0. That's a consequence of the fact that the process stopped at time t is a super martingale. Then, second thing you can prove using the fact that t is almost surely finite. So t almost surely finite is the assumption here. It's not the assumption there, but this is in fact a stronger assumption than almost surely finite. So in both cases, you can say that t is almost surely finite, and from that you can deduce this. The expected value of the limit when n goes to infinity of x and t is equal to, so I'm going to decompose this random variable by looking at indicator function on the event that t is larger than n, and indicator function on the event that t is less or equal to n. Now, you see that when n goes to infinity, this event here, this sequence of events here, t larger than n, because t is almost surely finite, this goes to the empty set. At the opposite, the limit of this sequence of events goes to omega. Okay? And so that tells you that in the limit, this part here, indicator function on the empty set that just 0, this part here disappears. Then at the opposite, this goes to indicator function on omega, that's the function equal to 1 everywhere. So this part kind of disappears and you just have the xt left. So in the limit, you get that this is equal to expected value of xt. All right, so that's what you can prove to begin with. Now you see that the goal is to prove that expected value of xt is less than the expected value of x0. Okay? But you have expected value of xt here and expected value of x0 here that we are able to re-express using those quantities. You just have an inequality here. So to conclude, what we need to prove is just that the limit of the expected value is equal to the expected value of the limit. Okay? If you look at, so here you have this is equal to that, but this one is less than x0. If you can prove that those two quantities are equal, then we get exactly this, and we are done. Okay, so, and you see that clearly that's a problem of exchanging limit and expected value, which is the same as exchanging limit and integral. Expected value is the integral with respect to the probability measure. So, how can we justify that the expected value of the limit is indeed equal to the limit of the expected value? We know two theorems that allows you to do that we saw in chapter 1. That's the monotone convergence theorem and the dominated convergence theorem. So, in this case, can we apply the monotone convergence theorem? Well, xnt is a super martingale, so it tends to decrease on average, but it's not clear that the sequence xnt is really decreasing. Okay? So it seems that we cannot use the monotone convergence theorem. So the only option left is the dominated convergence theorem. And then, at least in the first case, well, yes, we can use the dominated convergence theorem because we assume that the process stopped at time t, this xnt here, is bounded. So if it's bounded, well, that's bounded by a constant, but any constant is integrable because your measure in the background is a probability measure, so expected value of a constant, that's just this constant. And so in case number 1, because the process is bounded, you have indeed that those two quantities here, limit of the expected value and expected value of the limit, are equal by the dominated convergence theorem, because your process is bounded. So we get that. xnt bounded implies that the limit of the expected value is equal to the expected value of the limit, which by those two equation or inequalities here tells you that that we have indeed that expected value of xt is less than the expected value of x0. All right, so now, what about case number 2? Well, the idea to prove the second version of the optional stopping theorem is again going to be to apply the dominated convergence theorem, except that in this case, your process has bounded increments. So it's not clear that it's not bounded, okay? And so the application of the dominated convergence theorem is a little bit more difficult to justify. So what we need, if you remember the assumption of the theorem, it says that you can indeed exchange limit and expected value if we can find a function, let's say y, that is integrable and that dominates the absolute value of all those xnt. All right, so what we need to do is basically find like the best possible candidate for a bound for this process here and check that indeed this new Horner variable that dominates all those ones is indeed integrable. And so what we are going to do is look at this new random variable. It's clear that xnt is less than this random variable y equal to absolute value of x0 plus the infinite sum of the absolute value of xk plus 1 minus xk times the indicator function on the event that k is larger than k. So, why is it true? Well, clearly you can write the process as the sum of its increments, okay? And then what I'm using here implicitly is the triangle inequality, saying that the absolute value of the sum of the increments is less than the sum of the absolute value of the increments. That's exactly what I'm doing, okay? Now, I also have a t larger than k here. That's the same story as before. If t is less or equal to k, that means that we already stopped the process at time k, and so that means that this increment here is just 0, okay? At the opposite, if t is larger than k, then that means that at time k we did not stop the process yet, and so this increment here might be different from 0, okay? So by multiplying by this indicator function, I'm not really changing anything. Here I'm doing like two steps at once. Strictly speaking, what I should say is that this y is going to be equal to absolute value of x0 plus the infinite sum of xk plus 1 stopped at time t minus xk stopped at time t, but I can replace this increment for the process stopped at time t by the increment for the process that did not stop yet, but I need to multiply by this indicator function. All right, same trick as in the proof of the fact that this process is again a super martingale. We use this trick already. All right, so we have a natural bond for the absolute value of our process. Now, to justify that we can indeed again exchange limit and expected value, and so apply the dominated convergence theorem, what we need to prove is that y is integrable. To do this, you see that we have some increments here, so we are going to use the fact that we have bounded increments, and also we are going to deal with that. The infinite sum here is going to give you eventually a finite value because the expected value is finite. And in the proof, I'm going to use a trick that is very useful in probability theory in general, not just in this proof. And we are going to use again the same trick in the proof of the martingale convergence theorem. So the proof is here. I'm looking at the N1 norm of y. I want to prove that this is finite because it starts with some absolute value of x0, which is not going to move anyway. Just to simplify things, I'm just looking at the N1 norm of y minus N1 norm of x0. I end up with expected value of this quantity here. I want to prove that this is finite. So the first thing I'm doing is saying that the expected value of this infinite sum here is in fact equal to the infinite sum of the expected value. To do this, I'm using the monotone convergence theorem. Again, that's a trick we use. I think we use that in chapter 2. You just think of your infinite sum as the limit of the partial sums. Okay? But all the quantities in this sum here are positive, so that means that the sequence of partial sums is a monotone increasing sequence. And thinking of the infinite sum as this limit of a monotone sequence, you can use the monotone convergence theorem, and you use also in the background the fact that the expected value is linear, and eventually you can say that the expected value of this infinite sum is equal to the infinite sum of the expected value. All right, so we get this. Now, next step, I'm using the fact that, like this assumption here, the process stopped at time t as bounded increment, which means that on the event that t is larger than k, so the process hasn't been stopped yet, this increment here should be bounded by a constant. Let's call it c. Okay? If I call that C, then I can say that this expected value, okay, is going to be less than the expected value of C times this indicator function. Because the expected value is linear, I can put the C outside, and so that tells me that this expected value is less than C times the expected value of this indicator function. But the expected value of an indicator function is the probability of this event. Okay? And so eventually I end up with the fact that this is less than C times the infinite sum over K of the probability that T is larger than K. And now here is the trick I'm going to use that you can use across probability theory in general. That's a very useful result, and I'm going to use that again in the proof of the martingale convergence theorem. So that says that the infinite sum over K of the probability that T is larger than K is in fact equal to the expected value of T. That's true for any positive discrete random variable. You have the same result in the continuous case. Okay, if you have a continuous random variable that is also positive, but then the sum takes the form of an integral, that tells you that the expected value of T is in fact equal to the integral from 0 to infinity of the probability that T is larger than S, let's say ds. Okay? This is very useful in practice. Sometimes you want to compute the expected value, you don't really know how to do it, but you have those probabilities, and so that's one way you can compute the expected value. So the proof of that is interesting. You just say step one, well, the event that T is larger than K is exactly the same as the event that T is equal to K plus 1, or T is equal to K plus 2, or T is equal to K plus 3, and so on. And all those events are mutually exclusive, and so you can replace this probability that T is strictly larger than K by this infinite sum of the probability that T equals J for J strictly larger than K. Okay? So from a single infinite sum, you end up with a double infinite sum, like two infinite sums. Then at this point, you see that because this quantity depends on J and you sum over J, but this does not depend on K and this sum is over K, you kind of want to exchange those two sums here. And the way you do that is by using Fubini theorem that we saw in chapter 1. So Fubini theorem is about exchanging two integrals. Here you do not have integrals, you have infinite sums, but from the point of view of measure theory, a sum is the same as an integral with respect to the counting measure. Okay? So you can really think of your double sum as the same as a double integral. Okay? And because those probabilities here are positive, you are indeed in the condition where you can apply Fubini's theorem and say that the function you integrate is positive, so you can indeed exchange the two integrals. Okay, you can exchange the double integral. Here, that means that you exchange the double sum, and then you end up with, well, the sum over K of the sum over J larger than K becomes a sum over J of the sum over K less than J. Okay? Now, if you look at the sum over K less than J of this quantity, you see that this term here depends on J. But now you have a J fixed here in the sum, but you sum over K. But this does not depend on K. So this sum here is just P probability that T equals J that you add to itself exactly J times. Okay? That's the sum for K equals 0 to J minus 1. You have exactly J terms in this sum, and you add up this term to itself J times. So in fact, this sum here inside, this one was complicated to compute, but this one inside is just J times the probability that T equals J. Okay? And now you recognize infinite sum over J of J times the probability that T equals J. That's exactly the formula for the expected value. Okay? And so eventually, you end up with the fact that your L1 norm of y is less than L1 norm of x0 plus c, that's your constant, like your bound for the increment of your process, times the expected value of your stopping time. But by assumption, the expected value of your stopping time is finite. And so you end up with some quantity that is finite. So conclusion, the L1 norm of y is indeed finite. Y is a uniform bound for the absolute value of your process. And so you are in the condition exactly like before. You have the correct assumption so that you can use the dominated convergence theorem, and you can conclude exactly like here. You can exchange limit and expected value. And by those two expressions here, you end up again with expected value of xt less than the expected value of x0. So that completes the proof of the optional stopping theorem. So before we go to the approximate inequality, I just wanted to give you an example of application of that, or I should say a counter-example, because that's something very popular, and so that you understand how the theorem works. So this process, I'm going to call it the doubling bet process. So, and in fact, that's where the name, the word martingale comes from, okay? The word martingale in English, not in, like in English outside mathematics, describe a gambling strategy that consists in doubling your bet each time you play until you win. Alright, so that's basically, this process describes the actual word martingale people use in English outside mathematics. So the doubling bet process consists in betting $1 on the first coin flip. So I'm going to assume that in the background I just flip a fair coin. I'm using basically a particular case of a process I defined in the previous video, chapter 4. You remember we saw this process where you have a fair coin, you flip the coin. When you get heads, you win your bet. When you get tails, you lose your bet. And you can choose your bet that we call Bn at game number n. Okay? I'm looking at a particular example of that where you double your bet at each step, but you stop playing the first time you win. So what you do is the following. So you bet $1 on the first coin flip of a fair coin. If you get heads, then you win $1. If you get tails, then you lose $1. Then you keep doubling your bet, okay? And you stop playing after the first win. So that's a particular case of the betting random walk we defined in the previous video, where the bets are powers of 2, and your stopping time t, here you stop playing at some point, your stopping time t is going to be the first time you win. Okay, so eventually, mathematically, you can express the process like that. That's the betting random walk with the bet Bn is 2 at the power n minus 1. So meaning that at game number 1, you bet 2 at the power 0 equals $1. At game number 2, you bet $2. At game number 3, you bet $4 and so on. Okay? And you do this until Wn is equal to 1. So Wn is, in the previous video, the notation I use for the sequence of coin flip. Wn equals 1 means that at step 1 you get heads. And so t, your stopping time, is the first time n at which you get heads. So the first time at which you win. So what happens if you play this strategy? Let's assume that you lose 3 times and then you win for the first time at the fourth coin flip. Then you are going to lose $1 at the first coin flip. Then second coin flip, you are going to lose 2. And then third coin flip, you are going to lose 4. So you lose 1 plus 2 plus 4, that's 7. Okay? But at the next coin flip, you bet $8. And you are going to win those $8. So overall, you lost 7, but you win 8. So overall, you win $1. So playing this strategy, it seems that we get something that contradicts the theorem, okay? For the optional stopping theorem applied to martingale, we have an equation here. The expected value of the amount of money you have when you stop playing should be equal to the amount of money you had at the first place. This is not the case for this process, okay? You can prove that rigorously by using a conditioning on t. If you condition on t, you can say that, and now I'm using again y. Y is the notation I used for the betting random walk in the previous video. That's why I'm using this w and y here. You can easily prove that the conditional expectation of yt, given that t equals n, meaning that you first win at step n, is just equal to whatever you had at time 0, y0, minus everything you lost. What you lost is 1 plus 2 plus 4 plus 8 and so on, up to, well, you stop at 2 at the power n minus 2, okay? That's the bet at game n minus 1, but then you win at game n, and so you win 2 at the power n minus 1 dollars. Now, it's easy to prove that this sum here is equal to 2 at the power n minus 1, but minus 1. And so eventually, you end up with this is equal to y0 plus 1. So you win $1 in the process. So this is true for all n. And so clearly from that, you can easily deduce that the expected value of yt is always equal to y0 plus 1, or you can say expected value of y0 plus 1. That's just the next slide here. You just say that even if the process is a martingale, and so you have a fair game, the expected value of yt, you can compute it looking at the sum of those terms, but you multiply by this probability. Those terms are all equal to y0 plus 1. You end up with y0 plus 1 times the infinite sum of the probability that t equals n. But this infinite sum is just equal to 1. You add up the terms of a probability mass function, and so eventually you end up with y0 plus 1, which is not equal to y0. So that contradicts this theorem in the case of martingale. So why is that? Okay, why is it that we do not have the conclusion? Well, that means that somehow those assumptions are not satisfied. So let's see, so that's not really an example of application, that's more a counter-example to the theorem. So why we do not have those assumptions? Well, first let's look at the time t, okay? T is the first time at which you win. You use a fair coin, you wait until you get heads, okay? So clearly the number of coin flips you need to get heads is geometric with parameter 1/2. Okay, the geometric random variable keeps track of the first success if at each time step you have independently a success with probability p or failure with probability 1 minus p. That would be the geometric random variable with parameter p. Now your success probability, because you have a fair coin, is 1/2. So t is in fact a geometric random variable with parameter 1/2. This random variable has expected value 2, which is clearly finite. So you have the correct assumption for your stopping time. But the problem comes from the martingale stopped at this time. Even if you have a martingale, you see that the increments, they increase like power of 2, okay? And obviously, the time it takes until you win can be arbitrarily large, which means that your process yn stopped at time t does not have bounded increments. You do not have, like in the proof of the theorem, a little c that bounds all the increments of your process. That's why you do not have the conclusion of the optional stopping theorem. It's because the assumptions on the martingale are not satisfied. All right, so that's kind of the conclusion here. So that was more a counterexample we have expected value of t equals 2, but the increments are not bounded. That's why the optional stopping theorem does not apply. Now, it seems that when we see this counterexample, it seems that, well, we can indeed beat a fair game, okay, if we use this strategy. In fact, the answer is, well, not really. Why is that? Well, first, casinos, they know about this strategy, they know about the math behind, and if you go to a casino, you cannot play this doubling bet process strategy. It's not allowed, okay? So you cannot use that in a casino in real life. Now, you also have more mathematical results showing that, in fact, that doesn't really work. Here, in this case, you assume that you stop playing, okay, at the first win, and then on average, you win $1. This always works, okay, so you always win $1, but under the assumption that you can only keep playing and you still have money until the first win. And so, strictly speaking, that indeed works if you have an infinite amount of money. But if you start with $100 and that's it, there is a possibility that you run out of money before the first win, in which case you don't win $1, you lose your $100, okay? In general, what you can prove is that if you look at the betting random walk like that, with those bets, you remember those bets we said they should be Gn-1 measurable, which means that how much money you bet at game N should depend on your knowledge of the past. So, if you take the betting random walk, no matter how you choose the BN, and they can depend on the past as much as you want, but they cannot depend on the future, for any possible version of the betting random walk, you can prove that because the process is a martingale, if you just keep playing, you do not stop playing, you just keep playing, eventually you can use the martingale convergence theorem that we did not prove yet, but we are going to prove soon, to prove that eventually, because your process is a martingale, bounded in L1, your process is going to converge eventually to a limit, almost surely, and using that, you can conclude that eventually you hit 0. So, no matter how you choose your bet, okay, you can double your bet if you want, that can be your strategy. If you never stop playing, eventually you are going to hit 0. So how do you understand this result even if here you end up with $1 more? Well, the kind of intuition behind is that if you play this strategy once, you are likely to win $1, but if you keep playing this strategy, then eventually you are going to hit a very, very long string of failures in a row, of losses in a row, that's going to completely take all your money away and you cannot play anymore, okay? So what's dangerous in this strategy is that you may always have a long sequence of tails, a long sequence of losses, and those increments like increase exponentially fast, and that's going to take all your money away, and eventually even this strategy does not really work. So now let's see how we can use the optional stopping theorem to deduce the upcross inequality, and then use this inequality to prove the martingale convergence theorem. So first I need to define properly what we mean by an upcrossing or the number of upcrossing. So we fix two real numbers A and B. A is less than B. We can define the interval AB from that. That also appears in the picture here. And I'm going to call UAB the number of upcrossing of the process. The process in the background is exactly like before, a super martingale, but it can also be a martingale. All right, so here you have a picture of what we mean by an upcrossing. That's intuitively the number of times the process is going to cross the interval AB going up. So number of times you go from below A to above B. One way you can define properly the first upcrossing, in case this upcrossing happens, is using this kind of picture. So let's assume the process starts here between A and B. You wait until the process goes below A. you call that T1. T1 is the first time your process hits the interval negative infinity A. So that's a heating time, and so we saw that a heating time is indeed a stopping time. So T1 is the stopping time. Then, after, you are going to wait until the first time after time T1, your process is going to go above B, okay? I'm calling that time T2. T2 is the first time after a stopping time, your process hits the interval B plus infinity. So that's again, you can prove that T2 is again a stopping time, okay? So the time window here, T1, T2, corresponds to the time interval at which you see the first upcrossing, okay? And you can keep going like that and define the time window for second upcrossing, third upcrossing, and so on. So more rigorously, you can define the number of upcrossing like this by defining a sequence of stopping time, exactly like the T1, T2, but you keep on going. And then you can define the number of upcrossing like that. So what we are doing here basically is we fix T0 equals 0, and then we look at T1 is the first time after time T0 we go below A. T2 is the first time after T1 we go above B. And then if you look carefully at this expression, that means that T3 is defined as the first time after T2 you go below A. T4 is the first time after T3 you go above B, and so on. That's how this is defined. So those stopping times have different expression depending on whether you look at odd steps or even steps. Okay? So in general, any stopping time is defined as the first time after the previous stopping time you go either below A or above B. Okay? Like that, you can define your sequence of stopping time that will show you when the upcrossing of the interval AB occur, and you define the total number of upcrossing of your super martingale as the largest k such that T2k is finite. So, going back to the picture so that you understand this expression, let's assume, for instance, that after this point you never go below A ever again. That means that T3 is equal to infinity. It means that never, for all n larger than T2, okay, your process Xn will never be less than A. That tells you that T3 is equal to the infimum of the empty set, that's infinity. Okay? So, if you never go below A again, then T3 is infinite, which means that the largest k such that T2k is finite is k equals 1. And indeed, if you never go below A ever again, then that means that you had one upcrossing, but you are not going to have any other upcrossing in the future. Okay? So that's how you can define rigorously the total number of upcrossing. Then, now what the upcrossing inequality tells you is the following. I'm defining this new random variable here, UNAB, that's going to be the number of upcrossing of the interval AB, the same way we define that, but by time n. The reason why I cut at time n is because the goal after is to use, to apply the optional stopping theorem, and we saw that the optional stopping theorem only works when we deal with finite times, or almost surely finite times. And we saw also that eventually those stopping time might be infinite, and we are going to prove in fact that they are infinite eventually, because the number of upcrossing of any interval by a super martingale should be almost surely finite. So those stopping time eventually are infinite. And we don't want that, to be able to use the optional stopping theorem. That's why I cut at n. The upcrossing inequality tells us that for any integer k, the probability that the number of upcrossing is strictly larger than k is less than the expected value of the negative part of xn minus a, this process x is your super martingale, times the indicator function on the event that the number of upcrossing by time n is equal to k, divided by the length of this interval, that's b minus a. Okay, so that's what we want to prove. Again, this is a technical result that we use eventually to prove the martingale convergence theorem, but contrary to the optional stopping theorem, this result is not useful typically in practice. So how do we prove that? Well, first step, to simplify a little bit the algebra, observe that if xn is a super martingale, then xn minus a, that's just the process shifted like down by the value a, if a is positive, that's again going to be a super martingale. Okay? And so noticing that, you realize that, well, it's enough to prove the result for a equals 0. Okay? That's going to make that disappear, and the b minus a just becomes b. That's just to simplify the calculation, simplify the algebra. Right, so the first step of the proof is like some kind of inclusions among events that we are going to use after in some calculation. So notice that this event here is exactly the event there, the event of interest. I just replace the a by 0, which is our assumption now. And so I'm just saying that this event is the same as the event that t is less or equal to n. What is t? That's in the picture again. I slightly changed the picture. I changed the a by 0 here, that's our assumption. And then instead of a picture of the first upcrossing, assume that the processes started a while ago and we saw k upcrossing, and now we are seeing upcrossing number k plus 1. Okay? By definition of our sequence of stopping times, this upcrossing k plus 1 happens between time t to k plus 1 and t to k plus 2. I'm going to call those two times s and t, again to simplify the notation. Okay? And so clearly saying that we have more than k upcrossing by time n, that's exactly saying that this time t to k plus 2 that I call time t is less than n. Okay, we see that happening, and we see that happening before time n. That's exactly this event, t less than n. That's the first thing we are going to use. Second thing, obviously s is always less than t. Okay, they might be equal if they are both equal to infinity, but in general s is always less than t by definition. So clearly, if t is less than n, then s is less than n. That's an implication. So you have this inclusion of event that we are going to use, and also if t is less than n, that means that this upcrossing number k plus 1 indeed occurs. It's possible it never occurs, but on this event that shows that it indeed occurs, and it occurred by time n. And so by definition of those stopping times, at time t, the process must be above b. Okay? So that's this event xt larger than b. But here I'm just using instead not the process at time t, but the process at time minimum of t and n, which I can do because indeed the minimum of t and n is t, and so that tells me xt is above b, but that's the same as this event. Okay? So we have that in mind. If we see this upcrossing, we have strictly more than k upcrossing by time n, then this time must be less than n, and the process at this time must be above b. Alright, so using this now we can do some calculation and get this inequality. So the key step will be to use again the optional stopping theorem. So first, I'm going to look at this new quantity b times the probability that un0b is strictly larger than k. That's just this probability, but again, a equals 0. And you see here we divide by b minus a, that becomes just b. I multiply by b here. And so the goal is to prove that this is less than this expected value here, without the denominator. Okay, so first thing I can do is use linearity of the expected value and say that the probability of this event is just the expected value of the indicator function of this event, and then I can inject the b in the expected value. Okay, that's just what I do here. I just do that. Okay, then after we are going to use some of those inclusions. So first, what I can say is that by the fact that this set is a subset of this set, okay, I can say that on this event here, this random variable is larger than b. So I can replace the b here by this random variable, but then I have this inequality here, okay? Because this one is larger than this one. Okay, that's the next step that follows from this inclusion here. Then, next step, I'm just replacing, so I'm doing two things here. I'm replacing this random variable by its positive part. So why can I do that? Well, if you have a function, okay, any function, the positive part is the function that is equal to the function if the function is positive, but equal to 0 if the function is negative. So clearly, the positive part is larger than the function itself, okay? And so we indeed have that this is larger than that. Now, we also need to look at this indicator function here, but you see that by this inclusion, this event here is a subset of this one. And so indeed, this indicator function is less than that one. So what I did here is I just replace those two random variables by two other random variables that are larger. Okay? So indeed, we have this inequality here. All right, so now we are reaching like the key point of the proof. Notice that here what we want eventually is the negative part. But here we have the positive part instead, okay? So somehow we want to replace the positive part by the negative part, okay? And still have some inequality, okay? Now have in mind that the positive part is not larger or smaller than the negative part. It's possible that one is larger than the other one or the other way around, okay? We don't know that. So somehow we want to replace that by the negative part. For that, what we need to do is basically compare positive, like this quantity with the analog quantity, but when you have the negative part. But we know that positive part minus negative part is equal to your random variable itself. And so that's what we are going to do. We are going to look at positive part minus negative part, use linearity of the expected value to put everybody in the same expected value, go back to that, and then use the optional stopping theorem. That's kind of the key part of the proof. And so what we have is the following. By the optional stopping theorem, you can do the following. So first, I'm looking at this expected value here, okay, minus, well, the same expected value, but I'm looking at the negative part instead of the positive part, okay? You see by linearity, I can collapse like those two random variables inside the same expected value. Here, I'm just using linearity. I get expected value of positive part minus negative part times, again, this indicator function, okay? And then, clearly, positive part minus negative part is just equal to this random variable here. So I end up with that. Now, here is the key of the result. So, we want to prove that the expected value of the positive part is less than the expected value of the negative part. Okay? Which means that we want to prove that this difference here is negative. And so we want to prove that this part here is negative, which looks completely counterintuitive, because if you look at this random variable, that's the random variable here, it says larger than b. And you look at it on the picture, that's here. So how can this expected value be negative? That looks counterintuitive in view of the picture. But notice that here I have the event that number of outcrossing is equal to k, which means that in fact on this event, this does not happen. Okay, so you have to have in mind that maybe what I'm going to write looks counterintuitive, but that just because this inequality is in contradiction with this picture. But this picture is just a picture of something that may or may not happen. This inequality just says that this picture in fact is misleading because that shows the picture of an event that is not likely to happen. Okay, that's kind of the trick in the proof. So what I'm doing here is the following. I'm using the optional stopping theorem to go from this expected value to this one, where I replace the value of the process at time minimum of t and n with s. Okay? Looking at the picture, you say at time s, I'm below where I should be at time t. Except that, again, this is not likely. It's cost something for a super martingale to go up again. Okay? So, why is it true? Well, I'm using just a slight extension of the optional stopping theorem. We prove the optional stopping theorem to say that the expected value at a stopping time is less than the expected value at time 0. We can extend that easily to compare the process at two different stopping times, and we still have the inequality if there is an inequality among the stopping time. So now you see that the minimum of t and n is finite, okay? Even if t is infinite, we look at the minimum, n is fixed. So this is a finite stopping time, okay? S might be infinite, but we look at this on the event, like times indicator function on the event that s is less than n. So again, because of this indicator function, s is also finite, okay? So those two terms, minimum of t and n, and s are both finite stopping time. So we can use the optional stopping theorem, and clearly you see that the minimum of t and n, okay, on the event that s is less than n, this time is larger than time s, okay? So s is a stopping time that is smaller than that, okay? And so we have this inequality. On average, your super martingale goes down, so that means that the expected value at this time, which is larger than s, should be less than the expected value at time s, okay? So that's why we get this inequality that looks counterintuitive in view of the picture, but that's correct based on the optional stopping theorem. Then, how do we conclude? Well, then now you can really look at the picture and say that, well, by definition at time s, the process should be below a, but a equals 0. So this should be negative, okay? Now, obviously, it's not the case if s is infinite, but that's not possible because we look at only this random variable on the event that s is less than n, okay? So if s is less than n, that means that we were indeed able to go below a after, or below 0, after k upcrossing, and so indeed this s is finite and this random variable is negative, okay? So you have expected value of a negative random variable time an indicator function that's indeed negative. Alright, so all that was to just replace the plus here by a minus, okay? But that's everything that we need to get this. Then we have a few more steps. Then to conclude, we need to do this. So I'm going back to our starting point here. We know that it's less than this quantity, but we just proved here that we can replace the positive part by the negative part, okay? So that's why we have this term. This is less than this term because the difference is less than 0. Then, next step, I'm going to inject in this indicator function this new aspect, okay, that at time minimum of t and n, the super martingale is less than 0. Okay, so if I do this, I a priori reduce, okay, the value of my indicator function, and so I should not have an equal here. I should have that this is larger or equal to that. Why do we have equal? Well, that's just because, in fact, we take the negative part of this random variable. Okay? We don't look at this random variable itself, we look at the negative part. And so, on the event where this random variable is positive, this is just 0. Okay? So I just change my indicator function, but that doesn't change the whole expression because I just look at the set where this quantity is different from 0, is strictly positive. I just ignore the part where this is 0 because that doesn't change the expected value. So instead of an inequality that would go the wrong way, I indeed have an equation. Then, next step, here I'm saying that if at time minimum of t and n, the process is negative, so below A, that means that at this time we didn't have time to go above B. So that means that T maybe is finite, but at least larger than N. We did not see this upcrossing K plus 1. Okay? That's what it means, okay? Because if we indeed have that, then at this time we must be above B, which is positive, so that cannot be negative. So that explains the next inequality here. If we have this implies that T is larger than N. Okay? So we have this inequality. And then to conclude, you just notice that now we have a nice characterization of like, we understand already the number of upcrossing. If S is less than N, okay, that means that by time N we add K upcrossing, and then we also had time to go again below A. So that means that on this event, we had at least K upcrossing. But then we also have T strictly larger than N. So that means that we had K upcrossing. After upcrossing number K, we had time to go below A again. But T is larger than N, so we didn't have time by time N to go above B. Which means that, like, this implies that we add K upcrossing, but we don't have time to have one more. Okay? So, the intersection of those two events implies, like this and that, implies that we have exactly K upcrossing. And so eventually you end up with expected value of the negative part times this indicator function, which is exactly this expected value. I just replace the A by 0, okay? That's the same thing. And so eventually you get that indeed the probability that the number of upcrossing by time n is strictly larger than k is equal to this expected value that you recognize here, but divided by b here, which is the length of this interval. So that shows the upcrossing inequality. Okay, so now let's see how we can use the upcrossing inequality to deduce the martingale convergence theorem. So the theorem is here. I state the theorem for super martingale, but that's also true, obviously, for sub-martingale or martingales. We assume that we have a process Xn that is a super martingale bounded in L1. By that, I mean that the L1 norm of Xn is going to be bounded by a constant m that is finite and does not depend on n. Then in this case, Xn is going to converge almost surely to a random variable that is integrable. Right, so like I said previously, typically for stochastic processes, we only have convergence in distribution to what we call an invariant measure. Here we have something much stronger, convergence almost surely to a random variable. What this means is that for almost all realizations of your process Xn, the corresponding sample path is going to converge to a limit. We are not going to see those random fluctuations forever. Right? Obviously, because the convergence is not to a fixed deterministic limit, but to a random variable, the limit of your sample path may depend on the realization. Different realization may lead to different limits, but still, this shows that for almost all realization, your process is going to converge to a limit. So, how does it connect to the upcrossing inequality? And that's also going to tell you about the spirit of the proof. Well, if you take a sequence of real numbers, let's say, and you assume that this sequence does not converge, so you have those oscillations, then you can find a small interval AB such that your sequence is going to go from below A to above B infinitely often. Okay? At the opposite, if for all interval AB, your process is not going, or your process or your sample path or sequence of real numbers is not going to go from below A to above B, for any A and B, then that shows that eventually your process has to converge to a limit. That's kind of the idea. So the goal is to, like the key idea of the proof is to use the upcrossing inequality to show that for all A less than B, the probability that the super martingale is going to go from below A to above B infinitely often is equal to 0. So we want to basically have a bound on the probability of the number of upcrossing of any intervals. All right, so that's the spirit of the proof. So first step, I'm going to look at the expected value of the number of upcrossing of the interval AB by time n. What I'm doing here is I'm looking instead at the expected value, and I want to prove that the expected value is finite. If I can do that, that shows that this random variable is almost surely finite. Okay, that's a slightly stronger statement. Instead of proving to prove that a random variable is almost surely finite, it's enough to prove that its expected value is finite. Okay, now I'm not looking at the total number of upcrossing, I'm only looking at the number of upcrossing by time n to be able to use the upcrossing inequality that we just proved. Okay? Now obviously, if you cut at time n, the expected number of upcrossing is going to be finite, obviously, but notice that eventually the bound we get here does not depend on n. And so, because it does not depend on n, it's uniform in n. After, somehow we'll be able to take the limit and prove that the expected number of the total number of upcrossing is also finite. Okay, that's kind of the idea. So now, the different steps are, step 1, I'm going to replace the expected value by this sum of probability that this random variable is larger than k. This is the trick we used in the proof of the optional stopping theorem. So I remind you quickly, the idea was to write this probability as an infinite sum for j equals k plus 1 to infinity. Then we end up with a double sum. We can exchange the two sums using Fubini's theorem, and then we realize that this sum is indeed equal to this expected value. Okay, same trick as in the proof of the optional stopping theorem. That's step 1. Then step 2, well, why is it interesting to have the expected value written that way? Because this probability here is exactly the probability that appears on the left-hand side of the upcrossing inequality. So by just using directly the upcrossing inequality, I can just replace this probability by V, and I have this inequality, but I can say that this probability is less than the expected value of the negative part here times this indicator function divided by the length b minus a of my interval AB. Okay, so we get this. Then by linearity of the expected value, I can also inject the sum inside. Sum of the expected value is the expected value of the sum. And you see that eventually here I get sum over k of indicator function on V even that the number of upcrossing is equal to k. But notice that all those events for different values of k, they form a partition of omega. Okay? And so the sum of those indicator function is just equal to the indicator function of the union over k of those events, but the union over k of those events is equal to omega. So by injecting the sum inside, I basically replace like this sum of that by indicator function on omega, which is just equal to 1. So those two things, in fact, cancel each other. And I end up just with this expected value is less than expected value of negative part of xn minus a divided by b minus a. Then the last step is easy because the process is uniformly bounded in L1. I can just say that the expected value of this negative part is clearly less than this constant m plus absolute value of a, let's say, still divided by b minus a. For all a less than b, clearly this quantity here is finite. Okay? So that shows that not only the expected number of upcrossing by time n is finite, better than that, we have that it's bounded by a constant that does not depend on n. And so now we can take the limit when n goes to infinity to have a bound for the expected value of the total number of upcrossing. So how can we go from this inequality to, well, the same but with UAB instead? The idea is just to, again, exchange limit and expected value, and for that we can use the monotone convergence theorem. If you think of this random variable as part of a sequence of random variables that depends on capital N, then you get indeed a monotone sequence. If you increase n, then you are going to see potentially more upcrossing. So UNAB, as if you think of that as a function of n, that's non-decreasing, and so we can use the monotone convergence theorem and get the following. Okay, so because of this convergence and that's monotone, you can say that the expected number of upcrossing for all time is equal to the expected value of the limit of this random variable here. But expected value of the limit by monotone convergence theorem is the limit of the expected value. And so that's going to be less than the limit when n goes to infinity of this quantity, but this quantity does not depend on n. Okay, so you can get rid of the limit and you again obtain that the expected number of upcrossing at all time is going to be less than this constant, which is finite. From that, you deduce that the probability that the number of upcrossing is finite is equal to 1. Okay, right, so this is most of the proof. We have one last thing to prove. What we want to prove is something a little bit stronger than that. We want to, from the fact that the number of upcrossing of a given interval AB is almost surely finite, we want to prove that with probability 1, the number of upcrossing of any interval AB is going to be finite. So we want to go from a single event to a union of events. The problem is that if you look at a union over all AB real number, you end up with an uncountable union, and we don't want that in measure theory. Okay, so I'm going to use for the last step the same trick as what we use in a previous proof of the strong law of large number. In the case where we deal with random variable with finite variance, the proof based on the first Borel-Cantelli lemma. In this proof, we kind of replaced an uncountable union by a countable union by replacing basically R by Q. That's kind of the same trick we are going to use here. So the idea to conclude is here. So first, to prove convergence almost surely, what I want to prove is that the probability that xn does not converge to a limit is equal to 0. What does it mean that xn does not converge to a limit? Well, that means that the lim inf is different from the lim sup. The lim inf is strictly less than the lim sup. I defined those notions of lim inf and lim sup in chapter 1 when we talked about Fatou's lemma. And we saw that the lim inf is always defined. The lim sup is always well defined. But the limit only exists if the lim inf is equal to the lim sup. That's a typical result in mathematics. So looking at this event is exactly looking at the event, like looking at the set of little omega such that xn of omega does not have a limit. Okay? And I want to prove that this probability is equal to 0. If we do that, we have convergence almost surely. So first, to try to connect with this idea of upcrossing, I'm going to say that if the lim inf is strictly less than the lim sup, then I can find two real numbers a and b, a less than b, such that the lim inf is less than a, which is less than b, which is less than the lim sup. Okay? So this event is the same as this event here. Okay? But that's where we have basically a for some a, b in R that we don't like because that gives us some uncountable union. But clearly, because the topological closure of Q is equal to R, I can just assume that my A and B are just rational numbers. Okay? So what I'm saying is just that if the lim inf is strictly less, the lim inf is strictly less than the lim sup, if and only if there exists A and B rational number such that the lim inf is less than A, less than B, less than the lim sup. Okay? Then the last step is to observe that if indeed we have those inequalities, the saying that, interpretation of the lim inf of xn would be that your process xn is going to approach the lim inf infinitely often and is going to approach the lim sup infinitely often. So if you go close to this quantity and this one infinitely often, then that means that you are going to go below A infinitely often and above B infinitely often. So that means that the number of upcrossing of interval AB is going to be infinite. That's exactly what this event means. Okay? And so you can just say that this probability is also the probability that the total number of upcrossing is equal to AB, is equal to infinity for some A and B in the set Q of rational number. Now we are done because, well, first, because the total number of upcrossing is finite with probability 1, it's also infinite with probability 0. So those events have probability zeros, but then the for some A and B in Q is like a union over A and B in Q. So the probability of this union is less than the infinite sum of the probabilities. That's indeed a sum because Q is countable. And so eventually we end up with an event that is a countable union of events with probability 0. Okay? And so clearly this thing again has probability 0. So conclusion, the probability that xn does not converge, that's this event, okay, is equal to 0. So that means that the probability that xn converges to some value is equal to 1. That shows exactly that xn indeed converges almost surely to some random variable. So now let's prove that for a martingale, uniform integrability implies convergence almost surely and in L1 to the same random variable. So first, I'm giving you the definition of uniform integrability. You take a collection of random variables that does not have to be a sequence, that can just be a collection, a general collection of random variable xi, defined on the same probability space omega fp. We say that this collection is uniformly integrable if this limit here is equal to 0. So let's look more carefully at this quantity. We look at the expected value of the absolute value of xi on the event where absolute value of xi is larger than m. Okay? That defines a quantity that depends on I and m. Then you take the supremum over all I. Okay? And we want the limit of that when m goes to infinity to be equal to 0. That's what we mean by uniformly integrable. So, to understand a little bit more this concept, let's assume that we have only one random variable, capital X, let's say, that is integrable. And let's look at this quantity for this random variable in the limit when m goes to infinity. So, if x is integrable, then the L1 norm of x is finite, and so that implies in particular that x must be almost surely finite. Okay? So in particular, for such a random variable, the event that absolute value of x is larger than m should converge to the empty set when m goes to infinity. Okay? Which shows that if we have a single random variable that is integrable, the expected value of this quantity in the limit when m goes to infinity should just be equal to 0. Okay? But notice also that when you increase m, okay, you are going to decrease this event, and so you have monotonicity of those indicator functions as n varies, and by monotonicity, you can also use the monotone convergence theorem to put the limit outside, like here. Okay, so eventually what this shows, using monotonicity and the monotone convergence theorem, is that if you have a single random variable that is integrable, then the limit of the expected value of the absolute value of x on the set where absolute value of x is larger than m is equal to the expected value of the limit, which is equal to 0. Okay? So that shows that without the supremum here, if xi is integrable, then this limit is indeed 0. You can prove more generally from that if you take a finite collection of integrable random variables, then this collection is going to be uniformly integrable because all those limits are 0 and you just take the supremum over a finite set. But if you take an infinite collection of integrable random variables, then it's not clear that the full collection is going to be uniformly integrable. Okay? So that tells you a little bit more about this notion. Okay? So from this reasoning, you can deduce that if a collection of random variables is uniformly integrable, then each of those random variables is going to be integrable individually. Okay? But the converse is not true. If you take a collection of integrable random variables, then this collection is indeed uniformly integrable if this collection is finite, but maybe not if the collection is infinite. So that's a stronger statement than saying that we have a collection of integrable random variables. Alright, so now we understand a little bit better this notion of uniform integrability. The theorem we want to prove is the following. Uniform integrability implies for a martingale, okay, I need to precise that, that's not in the statement, but that's for a martingale. Uniform integrability implies that your process is going to converge almost surely, n in L1, to a random variable that is integrable. So, the idea to prove this theorem is to first look at convergence almost surely. For that, we only need to apply the martingale convergence theorem. The martingale convergence theorem says that we indeed have convergence almost surely to an integrable random variable if this martingale here is bounded in L1. But the fact that the martingale is bounded in L1 will follow easily from the fact that the collection is uniformly integrable. Now, once we identify this limit, that's the limit almost surely, next step is to look at the L1 norm of xn minus x infinity and prove that this L1 norm converges to 0, so that we also have convergence in L1 to this random variable. So step 1, we need to check the assumption of the Martingale convergence theorem, and basically we just get that. To prove convergence almost surely, we use the fact that because the collection is uniformly integrable, we can find M large such that the L1 norm of Xn is less than M plus 1, which is finite. So how do we do this? Let's look at the different steps here. So to prove this, the idea is just to decompose the L1 norm into like those two expected values. So on the set where absolute value of Xn is less than M, and on the set where absolute value of Xn is more than M. Notice that those two events are complement of each other, okay? Which means that the sum of those two indicator functions is just the indicator function on omega, that's the function constant equal to 1. So if you put together those two expected values using linearly, you get indeed that this is the expected value of the absolute value of Xn times the sum of the two indicator functions, which is equal to 1 everywhere. So you indeed get this. Okay, that shows the first equation. Now, to obtain that this is indeed less than something of the form m plus 1, which is finite, what you do is, first, you look at the second term and see that this is the same as this expected value here that appears in the definition of uniform integrability. So, this assumption tells you that this expected value here, uniformly in n, is going to converge to 0 as m goes to infinity. In particular, that means that you can find m large enough, but finite, such that this expected value, because it goes to 0, you can at least make it less than 1 by choosing m large enough. Okay? So step 1, you choose m large enough so that this is less than 1. That's possible by definition of uniform integrability. Now, once m is fixed, you can go to this term and see that that's the expected value on the event where absolute value of Xn is less than m. So clearly, this Xn here is less than m, and so this expected value is less than m times expected value of this indicator function. That's exactly m times the probability that the absolute value is less than m. But a probability is always between 0 and 1, and so that shows that this term is less than m. Okay? So eventually, after you get this decomposition, you can find m large but finite to make this term less than 1. Then this term will be less than m, so the sum is less than m plus 1, which is finite. Alright? And so notice also that so we have a bond for the L1 norm of Xn that does not depend on n, which means that the process indeed is bounded in L1, okay? And because by assumption that's a martingale, we can use the Martingale convergence theorem and deduce that this random variable Xn is going to converge almost surely to some random variable x infinity that is integrable. Alright? So that shows the first convergence. That's all we will need eventually at the end of this video to prove the strong law of large number. We don't need convergence in L1. But because we are almost there, I mean, now that we have identified the limit, that's just a tiny bit more work to also get convergence in L1, so I'm also going to do that. So, now that we have the limit, to prove convergence in L1, the idea is to look at the L1 norm of Xn minus x infinity. And so that motivates the introduction of a new sequence of random variable that I'm going to call yn. Yn is just the absolute value of Xn minus x infinity. And what we need to prove to have also convergence in L1 is prove that the expected value of yn goes to 0. Okay? So That's also why I'm fixing some epsilon positive here, maybe very small but still strictly positive. You fix such an epsilon. The goal is to prove that there exists n large enough such that the expected value of yn is less than, let's say, epsilon. Alright? So that's the goal. So for that, we are going to use two things first before we do some calculation. So first, notice that by assumption, this collection yn, this sequence yn, is uniformly integrable. This random variable x infinity is also integrable and it's fixed. Okay? So it's clear that from the definition that because those xn are uniformly integrable, yn also is going to be uniformly integrable. Okay? And so from that, you can just apply the definition and make this quantity here, but for this random variable yn, less than, let's say, this little epsilon, if you choose m large enough. So that's the first thing we do. Using the fact that yn, the collection yn, is uniformly integrable, we can say that for all n, there exists, I mean, no, it's not for all n there exists, is that there exists m such that uniformly in n, or for all n, the expected value of yn on the event where yn is more than m is going to converge to 0 when m goes to infinity, so be less than epsilon for some m large enough but finite. Okay? So that's the first step. Notice that, again, this is uniform in all n, which I can do by definition of uniform integrability. Then, step number 2, I'm going to use the fact that because xn goes to x infinity almost surely, okay, the difference here, xn minus x infinity in absolute value is going to go to 0 almost surely, but convergence to 0 implies also convergence in probability. That's what I proved in chapter 3. And so we can, like that, say something about the probability that yn is a little bit too big. And so basically we get that. Because we have convergence almost surely, which implies convergence in probability, we can say, and so this clearly goes to 0 almost surely and in probability, we can say that the probability that yn is larger than epsilon, okay, for all epsilon positive fixed, is going to go to 0, okay, this probability converges to 0 when n goes to infinity. In particular, now that we have our epsilon and m that are fixed, so epsilon is fixed here and m is fixed here and depends on epsilon, this, though maybe epsilon is small, maybe m is big, so epsilon over m is very small, but still they are both fixed and epsilon over m is strictly positive. So by convergence in probability, I can say that I can make this term less than epsilon over m for some n large. Okay, if n is large enough, I can make that less than epsilon over m. Okay, so now that we have those two things, I can now look at the expected value of yn, and I'm going to decompose this expected value on 3 sets. The set where yn is small, meaning less than epsilon, on the set where m is, yn is large, meaning larger than m, and on the set where yn is in between. And so eventually we get this. That's kind of the same trick as here. I just said that expected value of yn is the sum of those 3 expected values. Okay? Each term of yn times the indicator function on an event. Look at those events, that the event that yn is less or equal to epsilon, the event that yn is larger than epsilon but less or equal to m, and the event that yn is more than m. Those 3 events form a partition of omega. And so again, the sum of those 3 indicator functions is equal to the function constant equal to 1 on all omega. So using this and the fact that the expected value is linear, I indeed have that. So now let's look at each of those terms one by one and prove that indeed they are all 3 smalls. 3 small using those two properties. So first, what about the expected value of yn on the event where yn is less than epsilon? Well, clearly, because we're on the event where yn is less than epsilon, this expected value here is less than epsilon times expected value of the indicator function. That's epsilon times the probability of this event. A probability is between 0 and 1, and so that shows that this expected value here is less than epsilon. Okay? That's the first part. Now, second part, or I'm looking at the third one, it's easier, that's done here. Clearly, this one is less than epsilon, that's written here. That's by our choice of m. Okay? We chose m such that this is less than epsilon. So the first term and the last term are both less than epsilon. Now I'm going to use this one to control the term in the middle. So let's look at this expected value here. So looking at this expected value, you see that we are on the event in particular where yn is less than m. Okay? So I can say that this expected value, I can replace the yn by m, I get an inequality, I get the m outside, that's a constant, and the expected value is linear, and so this expected value is less than m times expected value of the indicator function, that's just m times the probability of this event. Okay? But the probability of this event is less than the probability that yn is more than epsilon, and we chose n large enough such that the probability that yn is more than epsilon is less than epsilon over m. And so eventually you end up with this expected value is less than m times the probability of an event, and this probability is less than epsilon over m. So this expected value in the middle is less than m times epsilon divided by m. That's again epsilon. So those three terms are each less or equal than epsilon. That shows that the expected value of yn is less than 3 epsilon for n large enough. So to recap, what we have is calling x infinity the limit almost surely of this sequence, and looking at absolute value of the difference here, we have that for all epsilon positive, even very small, we can find n large enough such that the expected value of yn, which is the L1 norm of xn minus x infinity, is less than 3 epsilon. Because epsilon can be chosen arbitrarily small, that shows that the L1 norm of xn minus x infinity goes to 0, and so that shows indeed that xn converges to x infinity in the space L1. So now let's prove that if a martingale is regular, then it must be uniformly integrable. Okay, so what we call a regular martingale is this type of process. We say that the process xn is a regular martingale if it can be written as the conditional expectation of x given gn. Gn is a filtration in the background, and x is a fixed random variable that is integrable. Okay, so it's not completely obvious that it's a martingale, but that's not very difficult to prove. So first, notice that by definition of the conditional expectation, this random variable here is gn measurable. So indeed, for all n, xn is gn measurable. So this process is adapted to the filtration gn. That's the first condition to have a martingale. The second condition tells you that the conditional expectation of xn plus 1 given gn should be equal to xn. So how do we prove that? Well, that's just by using the definition of xn, but also using the projection rule. So remember, I proved that when we covered chapter 2 about conditional expectation. If you look at the double conditional expectation of a random variable on two sigma algebras, one being a subset, sub-sigma algebra of the other one, it's the same as looking at the conditional expectation given the smaller sigma algebra. That's this property that we can use to prove that it's a martingale. And so indeed, if you look at conditional expectation of xn plus 1 given gn. You replace xn plus 1 by its definition. That's going to give you conditional expectation given gn of the conditional expectation of x given gn plus 1. If you look at gn and gn plus 1, because that's a filtration, the smaller of the two sigma algebra is gn. So this double conditional expectation is just the conditional expectation of x given gn. But by definition, the conditional expectation of x given gn is xn. So that shows that indeed, conditional expectation of xn plus 1 given gn is equal to xn. So that shows that a process that you can express like that is indeed a martingale, okay? And it's adapted to the filtration gn, so everything works fine. All right, so that's what we mean by regular martingale. So obviously not all martingales can be written that way, but this indeed defines a martingale. A possible way to visualize this process is to go back to the pictures I showed you to explain in chapter 2 the concept of conditional expectation. So I'm going to go back to those pictures. Let's assume that this painting of the Mona Lisa is your random variable x. Okay, I explained you can indeed think of this picture as a random variable in chapter 2. And then let's assume that here you have your filtration. So this one here, I mean Gn, here that's a picture of Gn, that's basically the Gn is basically the sigma algebra generated by those squares. And Gn plus 1 is the sigma algebra generated by those smaller squares. And so this sigma algebra is indeed larger than this one. So this one is a sub-sigma algebra of Gn plus 1. So you indeed have some kind of filtration. And then we saw in chapter 2 that one way you can visualize the conditional expectation of x given Gn, okay, is by looking at this picture, okay, when you have same color on each of those little squares, and that's the average of colors in this picture. So that would be a picture of the conditional expectation of x given Gn, which is xn. And then same story, you can visualize xn plus 1 looking at this picture. Okay, so eventually that gives you kind of the idea of what is a regular martingale. That's the intuition behind. You have basically a random variable x that is integrable, that is fixed, and then you have this sequence of sub-sigma algebras of f. That sequence is non-decreasing, and so you have indeed a filtration, and as time goes, you see your picture more and more. Okay, that's one way to think of a regular martingale. All right, so now the theorem we want to prove is that if a martingale is regular, then, so of this form, then it should be uniformly integrable. Okay, so I'm reminding you here the definition of uniform integrability. This limit should be equal to 0. That's what we want to prove. All right, so to prove that, step 1 is just to remind the definition of a regular martingale. So I'm going to fix some x in L1, integrable. I'm going to fix a filtration, and we are going to write xn as the conditional expectation of x given Gn. So we just do this. Now, using the fact that x is integrable, you can say the following. You can say that basically the L1 norm of x is finite, and so if you take any even b with a small enough probability, you can make this expected value here, that is more or less the L1 norm, but on the event b only, you can make this expected value as small as you want, okay? If you take that even b, like the probability of this event small enough. All right, so eventually we get that for all epsilon positive, we can find delta, maybe very small but strictly positive, such that for any even b with probability less than delta, the expected value of the absolute value of x on the even b is going to be less than epsilon. Okay? Then next, to finish the proof, I'm going to use two important inequalities. The first one is Markov's inequality, the second one is Jensen's inequality. I prove those two inequalities when I cover chapter 3 of my book about the convergence of random sequences of random variables. So first, we use Markov's inequality like that. The goal is, the target is that now I'm fixing an M, large enough such that eventually this quantity for my martingale here is going to be less than this epsilon. Okay? And so for that, I'm taking M larger than the L1 norm of X divided by delta. X is in L1, so indeed this L1 norm is finite. Delta might be very small, but it's strictly positive, so this quantity is indeed finite. It might be large, but it's finite. Now, I'm taking an M, any M, but fixed that is larger than that. Then, I remind you that Markov's inequality tells you something about the probability that a positive random variable is larger than a number. The probability that this random variable is larger than something is less than the expected value of your random variable divided by the something. Here, I'm applying that to this random variable, conditional expectation of absolute value of x given Gn, okay, larger than this M here. Okay, I'm looking at this quantity. Notice that this conditional expectation is indeed a positive random variable because I'm taking the absolute value of x. Okay, so Markov's inequality tells me that this probability should be less than the expected value of this conditional expectation, okay, divided by m. That's what I have here. But another property of the conditional expectation that I proved in chapter 2 says that the expected value of the conditional expectation is just equal to the unconditional expectation of your random variable. So in fact, this expected value here is just the expected value of absolute value of x. That's the L1 norm of x. Okay? So eventually I get that probability of this event is less than L1 norm of x divided by m. But look at the way I chose m. Okay? M is larger than the L1 norm of x divided by delta, which means that the L1 norm divided by m is less than this little delta here. Okay, that's the way it's designed, that's why we choose m like that. Next step, notice that now I have an event here with probability less than delta. So I'm in this context, I'm indeed in the context where I have an event with probability less than delta, and so I can say by this implication that this is true, this expected value is less than epsilon if I replace this indicator function on B by indicator function on this event, this conditional expectation larger than m. So I'm getting closer to that, and so we get exactly this. Okay? Here again, I'm using the fact that the probability here is less than delta, so I can replace B here by this event. All right? So, to conclude, you notice that we have kind of something that looks like this expression here, except that we have this absolute value of x that is fixed. Instead, we want some xn. And so to be able to replace absolute value of x here by somehow absolute value of xn, what I'm going to use is the following. It's Jensen's inequality that says that absolute value of xn, which by definition is equal to the absolute value of the conditional expectation of x given Gn, I'm just replacing by the definition, is going to be less, by Jensen's inequality, is going to be less than the expected value of the absolute value of x given Gn. So I remind you that Jensen's inequality that I proved in chapter 3 tells you that if f is a convex function, then f of the expected value of x is less than the expected value of f of x. Okay? I proved the result only for unconditional expectation, but that also works for conditional expectation. Here I'm using Jensen's inequality for the convex function absolute value of x that looks like that. That's a V shape. That's indeed a convex function. Okay? So you get that from Jensen's inequality. So what's important is that the absolute value of xn that appears here and here, in fact in the definition of uniform integrability that I have here, is in fact less than this random variable that appears here. Okay? So from that, I can conclude and say that the expected value of absolute value of xn on the event where absolute value of xn is larger than m, so basically I'm looking at the analog of this quantity, but for the martingale xn, is less than, well, the same expected value, but here I just replaced absolute value of xn here and here by this conditional expectation of absolute value of x given gn. So why can I do that? Well, indeed, this is less than that. And also, you see that if absolute value of xn is larger than m, then also this conditional expectation is going to be larger than m. So not only I increase going from here to here, I indeed increase the random variable, but also this indicator function here is indeed less than this indicator function here. So I indeed have this inequality. Then, exactly like we did before, I'm going like to go from here to here. I'm using the same property here of conditional expectation, saying that the expected value of a conditional expectation is equal to the unconditional expectation of the random variable. So I can replace this conditional expectation here by just the absolute value of x. But then if you look at this quantity here, you just recognize exactly this expected value here, and we prove that it was less than epsilon. Okay? So to recap, you see that we start with a process that takes the form of a regular martingale. Then we take some epsilon that can be whatever, that can be arbitrarily small but strictly positive. And then along the way, we can find an m large but finite, such that this quantity, which is the same as here, is going to be uniformly in n, okay, is going to be less than epsilon. And that's true for all m larger than this quantity. And so that shows indeed that that uniformly in n, this expected value here is less than epsilon, that can go to 0. And so this shows that the supremum over n of this expected value goes to 0 when m goes to infinity, exactly like here. And so conclusion, our regular martingale indeed is uniformly integrable. So now let's prove that if a process is a reverse martingale, then it's going to also be a regular martingale. In particular, based on what we proved before, we can also deduce that a reverse martingale is going to converge almost surely n in L1, and we can give some expression of the limit. All right, so here is the definition of a reverse martingale. That's basically the same as a martingale, but the process is indexed by negative time instead of being indexed by positive times. So some people would write the process xn for n negative instead to underline the fact that time now is negative. I'm going to write the process x sub minus n with n positive. Okay, so we say that this process is a reverse martingale, okay, if we have a filtration here. Okay, so now in this filtration, you have to understand that things go backward, okay, that's reversed. So G0 is going to be the largest sigma algebra, G1 is smaller, G minus 1 is smaller, G minus 2 is smaller than G minus 1, and so on, okay? So the limiting sigma algebra when n goes to infinity, that's the sigma algebra that I'm going to call G minus infinity. That's the smallest one, the one far in the past. Okay, so we said that this process is a reverse martingale if it's adapted to this filtration indexed by negative time, and if the conditional expectation of x minus n given g minus n plus 1 is equal to x minus n plus 1. Okay, so that's exactly the same definition as a normal martingale, but you need to think a little bit because now your time is negative, so things go a little bit backward in time. So now what's going on in this type of process is that typically for a typical martingale, you would start at time 0 and go to time plus infinity, okay? So your limiting sigma algebra is the one at plus infinity, that's the largest sigma algebra. Here at the opposite, when n goes to infinity, your minus n goes to negative infinity, okay? And so your limiting sigma algebra, that's the one far in the past, okay? And that's not the largest one, that's the smallest one, okay? So I have a picture here to show you a little bit what's going on and the theorem we want to prove. Here, basically your martingale, instead of going from time 0 to time plus infinity, it goes from time negative infinity to time 0, okay? And so the limiting sigma algebra is the one far in the past, okay? So here you have kind of a picture of what's going on with this filtration and those sigma algebras. G0 is going to be the largest sigma algebra in your filtration. That's the knowledge of everything, okay? And then when n increases, your negative n is going to the left, is going to decrease. And g minus n is your knowledge of everything that happened in the far past, time negative infinity, up to time negative n, okay? And I'm going to call g minus infinity, that I represent by a point here to say the limiting sigma algebra in the past, that's going to be basically the intersection of all those sigma algebras, g minus n. Alright, so now things go backwards, reverse, and so on. Start from negative infinity up to time 0 instead of going from time 0 to time plus infinity. And the theorem we want to prove is the fact that for a reverse martingale like that, your process is going to converge almost surely in L1 to a random variable that I'm going to call x minus infinity. This random variable is in fact equal to the conditional expectation of x0 given your limiting sigma algebra here, far in the past. Alright, so I also remind you what we just proved, like the previous two implications we proved. We proved that uniformly integrable implies that for a martingale that your process converges almost surely and in L1 to an integrable random variable. And also what we just proved before is that a regular martingale is also a uniformly integrable martingale. So if you put everything together, you see that regular implies convergence almost surely and in L1. And so to prove this theorem, the first step is going to be to prove that a reverse martingale is a regular martingale. And then you can use those two implications and deduce that we indeed have convergence. Then there will be one more step that we need to prove that the limit indeed is of this form, that's indeed the conditional expectation of x0 given this limiting sigma algebra. Alright, so how can we prove that it's a regular martingale? And there is some kind of intuition behind. Remember that a regular martingale can be written as expected value of a fixed random variable given your sigma algebras in your filtration. Here, kind of your target that you have in mind, what you know eventually, that's x0, okay? That's not a limiting object, that's just x0. So intuitively, we kind of expect, okay, that based on this definition, we kind of expect that x minus n should be equal to the conditional expectation of x0 given g minus n. And if it's true, that's indeed going to prove that a reverse martingale is a regular martingale, and we can deduce that. Okay, and indeed that works. And to do this, to prove this, we just use again the projection rule several times. So, like I told you, what we expect is that x minus n is equal to the conditional expectation of x0 given g minus n. Okay, that's what we want to prove. The proof is here. So I'm going to start from this conditional expectation. That's the best candidate we have in mind for x minus n. Notice that indeed that's the conditional expectation of a fixed random variable, x0, that is integrable given your sigma algebra at time negative n. So that's indeed of the form of a regular martingale. So how do we prove, how do we get from here to here? Well, that's by using the projection rule. So first, I'm going to say that I do not change anything if I replace x0 by the conditional expectation of x0 given g minus 1. So why is that? Well, you see that here I have a double conditional expectation. I condition on g minus 1 and then g minus n. We saw in chapter 2 properties of the conditional expectation that you have this property called the projection rule that says that if you have a double conditioning with one sigma algebra that is a sub-sigma algebra of the other one, then that's the same as conditioning on the smaller sigma algebra. In this case, because things go backward, g minus 1 is a larger sigma algebra than g minus n, so the double conditioning is the same as conditioning only on g minus n, which is what you have here. Okay? So indeed, this is equal to that by the projection rule and the fact that g minus n is a sub-sigma algebra of g minus 1. Alright. Now, if you look at this expression here, you see that this is exactly of this form. Okay? That's exactly this conditional expectation here, but for n equals 0. And so by definition, this should be, by the definition of martingale, that should be equal to x minus 1. And so I can just replace this by x minus 1. Alright, so you see, we went from this expression to this one. I was able to replace x0 by x minus 1. The only thing we use in this step is the fact that we condition on a sigma algebra that is larger than g minus n, so we cannot use induction and keep doing that forever, but we can at least keep doing that up to time negative n, okay? And so you can say again that using the same reasoning, you condition on g minus 2, and then you inject an x minus 2 here, and so on. And eventually you end up with the fact that this is also equal to the conditional expectation of x minus n given g minus n. But by definition, because x minus n is adapted to this filtration, x minus n is g minus n measurable, and so you are in the case of perfect information that we saw in chapter 2, and so this conditional expectation is just x minus n. Alright, so that shows that x minus n can indeed be written in the form conditional expectation of a fixed random variable that is integrable given g minus n, which is your filtration. And so that shows that our reverse martingale is indeed a regular martingale. Okay, so now from that we can deduce convergence almost surely n in L1. Okay, so this is a regular martingale, and so using those two implications, we deduce that we have convergence almost surely n in L1 to a random variable x minus infinity, that's the one here, that is g minus infinity measurable. So now we still have some work to do. We only have convergence almost surely n in L1. We need also to prove that the limit is of this form. The limit is indeed the conditional expectation of x0 given this limiting sigma algebra here, far in the past. So for that, we need to prove two things. If you remember the definition of conditional expectation, saying that this is indeed equal to the expected value of x0 given g minus infinity, that's the same as saying that this random variable is g minus infinity measurable. That's condition 1, measurability condition. Condition 2, we want to prove that the expected value of x minus infinity and the expected value of x0 are equal on all sets, all measurable sets in this limiting sigma algebra. Okay, that's the two things we want to prove. I already wrote one of the two, the first condition. I already say here that the limit here must be g minus infinity measurable. So, why is it true? Well, you can see clearly that this is like the x minus n is g minus n measurable. In general, you can say that the limit should be g minus n measurable for all n. And so that means that it should be measurable for the sigma algebra intersection of all those g minus n here, okay? So basically the preimage by this limit of any Borel set should be in all the g minus n, so that should be in the intersection of all of them. But the intersection of all of them, by definition, that's what I call g minus infinity. So we have the first condition here. Second thing we want to prove, like I told you, is that x minus infinity and x0 should be equal on, the expected value should be equal on any set in g minus infinity. Okay, that's the second condition, that the second part of the definition of conditional expectation. So to prove that, I'm going to take a set A in g minus infinity, okay? And I want to prove that expected value of that on the set A is equal to expected value of x0 on the set A. So by definition, because g minus infinity is the intersection of all those sigma algebras, what we can say is that A should be in g minus n for all n positive. All right. So from that, I can deduce the following. I can deduce that the expected value of x0 indicator function on A is equal to the expected value of x minus n indicator function on A. Why is it true? And it's true for all n. So why is it true? Well, because A belongs to g minus n, but what we proved here also is that x minus n is the conditional expectation of x0 given g minus n. And so again, by definition of the conditional expectation, this equals that implies that for all a in g minus n, the expected value of x0 and the expected value of x minus n should be equal on any set A in g minus n. That's exactly what I have here. A is in g minus n for all n. So this must be equal to that. Right? So something interesting that we have here is the fact that if A is in this limiting sigma algebra, what we have is that this quantity that a priori depends on n is in fact just equal to the expected value of x0 times indicator function on A. So that in fact does not depend on n. Okay? So using this we can go further and eventually conclude. So now the goal, like I said, is to prove that this is equal to that. Okay? That's the other condition we need to prove that this limit is indeed equal to this conditional expectation. And so I'm looking at the absolute value of the difference of those expected values. Because this is always equal to that for all n, I can just replace this by this expression and take the limit, okay? It doesn't matter, this is always equal to that, so it's still true in the limit. So I can just take the limit and replace the x0 by x minus n. Okay, then next step, I'm again going to use here Jensen's inequality, like in the previous proof, using the indicator function. So I'm doing several things at the same time here. What I'm doing here is I'm just saying that the difference of those two expected values bilinearly is the expected value of the difference. So that's expected value of x minus n minus x minus infinity times indicator function on A. And I have the absolute value of that. But the absolute value function is a convex function. And so I can use Jensen's inequality to say that this is less than the expected value of the absolute value of x minus n minus x minus infinity that I have here, times indicator function on A. But the indicator function on A is just a function between 0 and 1. So that's less than 1, okay? And so using all those inequalities, okay, linearity of the expected value, Jensen's inequality, the fact that an indicator function is less or equal to 1, using all those things, I end up with the fact that this quantity here is less than the limit when n goes to infinity of the L1 norm of x minus n minus x minus infinity. So now, how do we conclude? Well, go back to here. We already proved here that because this reverse martingale is a regular martingale, it's going to converge almost surely n in L1, that's the part that is important, to this random variable x minus infinity. So convergence in L1 in particular means that the L1 norm of x minus n minus x minus infinity should converge to 0. That's exactly what we have here. This is the L1 norm of x minus n minus x minus infinity. By convergence in L1, we deduce that this limit here is equal to 0. Okay? So, conclusion, we have a quantity here that does not depend on n, but then somehow we can make it dependent on n, take the limit and so on. We get limit equals 0, and so eventually we get that this absolute value here is 0. And so we deduce that this expected value here is equal to this expected value. That's true for all A in this limiting sigma algebra. This and the fact that g minus infinity, x minus infinity is also g minus infinity measurable implies that x minus infinity is indeed equal to the conditional expectation of x0 given g minus infinity. So that's the conclusion here. We have that, and so indeed that shows this theorem here. Now to conclude this video, I'm going to give you two applications of the theory of martingale. And first, I'm going to show you how you can prove what we call Kolmogorov 0-1 law using the martingale convergence theorem. So, to state the Kolmogorov 0-1 law, I need to start with a sequence xn of independent random variables. Those random variables do not have to be identically distributed. And I'm going to define different sigma algebras. So the plus sign here, and then after I'm going to define sigma algebras with the minus sign. So the plus sign means future, basically, things in the future. The minus sign will mean things in the past. So I'm defining this first sigma algebra for all n. F plus n is the sigma algebra generated by xn, xn plus 1, xn plus 2, and so on. So this sigma algebra represents your knowledge of the sequence in the future starting from time n. Okay? Now notice that as n increases, your sigma algebra is going to decrease. Okay? And so the intersection of all those sigma algebras is again a sigma algebra. Okay? The limit of that when n goes to infinity is the intersection of all the sigma algebras. That's a sigma algebra. That's what I call F plus. So F plus n is your knowledge of the sequence starting from time n. F plus is basically your knowledge of the sequence in the limit in the future. All right. So now that we have that, I can state the theorem or Kolmogorov 0-1 law. So it says that for every event A in F plus, then the probability of A is going to be either 0 or 1. So an event A in F plus is also called a tail event. So why is that? Well, you see that if A is in F plus, then that means more or less that the occurrence of A, whether A occurs or not, is not going to change if you change the outcome of only a finite number of those xn. So that means that whether A occurs or not depends on the tail of the sequence. Okay? That's why we call that a tail event. Okay? So if you have a tail event, then this event must have probability 0 or 1. Notice that there are some similarities between this theorem and the two Borel-Cantelli lemmas. In the Borel-Cantelli lemmas, instead of a sequence of random variables that are independent, we looked at a sequence of events that are independent. And the particular event we study in the two Borel-Cantelli lemmas is the lim sup of the AN, which is the event that AN occurs for infinitely many n. If you change the occurrence of only a finite number of the AN, you are not going to change whether the lim sup of the AN occurs or not. So the lim sup of the AN in the two Borel-Cantelli lemmas was already some tail event. Okay? So here we have some similarities with the two Borel-Cantelli lemmas that I proved in chapter 3. Right, so instead of proving just this result, I'm going to prove a stronger theorem, something that directly implies Kolmogorov 0-1 law, because that's what we are going to need after to get a proof of the strong law of large number. So more precisely, what I'm going to prove instead is this theorem. Assume that x is a random variable that is integrable and f plus measurable. Then this random variable must be almost surely constant. So why is it true that, why is it clear that this theorem implies Kolmogorov 0-1 law? Well, you just have to apply this result to the function x equals indicator function on your tail event A. Okay, so indeed an indicator function is obviously, the expected value of that is probability of A, that's between 0 and 1, so that's indeed integrable. Okay, because A is in F plus, indicator function on A is indeed F plus measurable. So the condition, the assumption of this theorem are satisfied. And so by this theorem we conclude that indicator function on A is almost surely constant. But an indicator function can only be equal to 0 or 1. So that means that indicator function on A is always equal to 0, in which case P of A equals 0, or always equal to 1, in which case P of A equals 1. So you indeed have this conclusion. Okay? So the theorem is indeed a stronger result than Kolmogorov 0-1 law. So now, how do we prove the theorem? Well, the goal, like I said, is to use the Martingale convergence theorem. So first we are going to identify somewhere a martingale, prove that this martingale is bounded in L1, and then conclude that we have convergence almost surely. Okay? And we need to prove that the limit is constant. All right, so first I'm going to define more sigma algebras. So first I'm going to look at the natural filtration of this process. Okay, f minus n is going to be the sigma algebra generated by x0, x1 up to xn. That's the natural filtration of the process. That's contrary to this one, which is your knowledge of the process in the future starting from time n. This one is your knowledge of the process in the past between time 0 and time n. Okay? And then, same story, I'm going to look at some kind of limiting object. I'm calling f minus here the sigma algebra generated by the union of all those sigma algebras. Okay? So, in picture that looks like that, you can kind of have this picture in mind. If this is time n here, and you have your sequence in the background, f minus n is your knowledge of everything that happened between time 0 and time n. F plus n is your knowledge of everything that happened starting from time n in the future. F minus is your knowledge of everything. F plus is only your knowledge of the far future, like the tail of the sequence. All right. So then I'm going to define a new process, yn, that is going to be equal to the expected value of x, so that's this random variable x here that is integrable and f plus measurable, given the sigma algebra, the nth sigma algebra in your filtration. Okay, and also, yeah, I defined already this sigma algebra. So now it turns out that this process yn is a martingale. You can prove that like we did before using the projection rule. So we need to check that this conditional expectation is indeed equal to yn. So for that, step 1, I'm just going to replace yn plus 1 by its definition. So that's conditional expectation of x given f minus n plus 1, okay? But then I can use the projection rule and say that because this sequence f minus n is increasing, of those two sub-sigma algebras of f, fn is the smallest one. And so by the projection rule, this double conditioning is the same as the conditional expectation of x given fn only that we have here, but this by definition is yn. So that shows that indeed yn is a martingale. Okay? And then next we want to prove that this martingale is bounded in L1 to be able to apply the martingale convergence theorem. This can be done by using again Jensen's inequality like we did several times before, and we apply this inequality again to the convex function absolute value of x. So I'm looking at the L1 norm of yn. I want to prove that this is bounded by a quantity that does not depend on n to be able to apply the martingale convergence theorem. So by Jensen's inequality, so first I could say that expected value of the absolute value of yn is expected value of the absolute value of that conditional expectation, but absolute value of this conditional expectation is less than the conditional expectation of the absolute value. Okay, so that gives me this. But again, chapter 2, property of the conditional expectation, the expected value of a conditional expectation is just the expected value of your random variable here. So that's equal to the L1 norm of x. X is fixed. For all n, the L1 norm of yn is less than the L1 norm of x, which is finite because x is integrable. Okay? This is fixed, that doesn't depend on n, so this process, this martingale is indeed bounded in L1, and so by the martingale convergence theorem, I can deduce that yn, which is this, I just remind you the definition, is going to converge almost surely, exactly like for reverse martingale. You can prove, you can see that the limit is going to be f minus measurable, and so that's going to converge, in fact, to the conditional expectation of x given f minus. Right. So here I proved several things that, in fact, we just proved before a little bit, looking at regular martingales or not. I just wanted to have a proof that only follows for the martingale convergence theorem, but we could go faster, noticing from this step that yn is the form conditional expectation of a fixed random variable that is integrable, given the elements of a filtration, so given those sigma algebras, and clearly that means that yn is a regular martingale, and we saw that for a regular martingale, we have convergence almost surely and in L1. So this convergence almost surely, in fact, we can have it already from here, using what we did before about regular martingale. So here I'm just using again tricks that we saw before, projection rule, Jensen's inequality. All right. So Now, the last step is to use this convergence to prove that indeed x is going to be constant almost surely. So for that, the trick is going to be to use that x is f plus measurable. But you see that here we have a conditional expectation given f minus n. F minus n, you see that's your knowledge from time 0 to time n. F plus is your knowledge of the far future. So that means, and because those random variables here are independent, the fact that you explore looking at those sigma algebras, you look at disjoint parts of time and things are independent, you see that f minus n and f plus are independent. Okay? But this converges almost surely to the conditional expectation of x given f minus. And f minus at the opposite, that's your sigma algebra that represents the knowledge of everything. That's the sigma algebra generated by the union of all the f minus n. And so from that you can also say that f plus is a sub-sigma algebra of f minus. So you see that in this quantity you have a random variable that is f plus measurable that is independent of that. At the opposite, in this limit, you have this random variable that is f plus measurable that is also f minus measurable. And using this, you can indeed conclude that basically x is equal to its expected value almost surely. And so that shows that x is almost surely constant. So how does it work? Well, you just say the following. I remind you that x is f plus measurable. Then clearly f plus and f minus n are independent. Okay? F plus depends on the far future. F minus n is your knowledge of the first n. Those things are independent. Those xn are independent. So those two sigma algebras are independent. This tells you that this conditional expectation is just equal to the expected value of x. Here I'm using techniques results that are improved in chapter 2 about conditional expectation, because in the random variable in your conditional expectation is independent of your sigma algebra. You are in the case of no information relevant to understand x. So the conditional expectation is equal to the unconditional expectation of your random variable. So this is equal to the expected value of x. This shows that for all n, yn is just equal to the expected value of x. Okay? That follows from the fact that x is f plus measurable. But then, that means that this sequence is constant. Okay? So if it's constant, it should converge to the limit almost surely should just be equal to this constant. And so the last step is to look at the limit and say, well, this limit should also be equal to the expected value of x. But this limit, now at the opposite, we are in the case of perfect information. Okay? F plus is a sub-sigma algebra of f minus. F plus is your knowledge of the far future. F minus is your knowledge of all the sequence. So f plus is a sub-sigma algebra of f minus. And so that means that x, which is f plus measurable, is also f minus measurable. And so in this case, like here you have independence, here at the opposite, x is f minus measurable, so you are in the case of perfect information, again, properly that I proved in chapter 2. In this case, because x is f minus measurable, conditional expectation of x given f minus is equal to x. Alright? So eventually you get that yn is constant equal to the expected value of x. But as almost surely limit x, that shows that the limit x is equal to the expected value of x, which means exactly that x is constant almost surely. That's the conclusion that we have here. So indeed, that shows the theorem and also Kolmogorov 0-1 law. Finally, let's combine Kolmogorov 0-1 law and reverse martingale to get a proof of the strong law of large number. So I remind you the statement of the strong law of large number. It says that if you have a sequence xn of independent, identically distributed random variables, so because they are identically distributed, in particular, they have the same mean mu, or same expected value, then in this context, the empirical mean, what I call the empirical mean, is going to converge almost surely to the theoretical mean mu. The empirical mean is just the average of the first n random variables. That's x1 plus x2 up to xn divided by n. That's a random variable, but when n goes to infinity, this quantity in the limit basically converges almost surely to a deterministic number, which is the theoretical mean. I already proved this result in chapter 3. The proof was based on a combination of Chebyshev's inequality and the first Borel-Cantelli lemma. But to be able to apply Chebyshev's inequality, you need to assume that those random variables xi have a finite variance. Okay? So we could only prove the result under this restriction, finite variance. Now, using those tools, we can, in fact, prove the stronger version where the xi can have an infinite variance. So, the first step is to find somewhere a reverse martingale, okay? And then argue that this martingale is going to converge almost surely to a limit. So, of course, because we want to prove that the empirical mean here is going to converge to a limit, we kind of want to say that, well, maybe Sn over n is indeed a reverse martingale. And indeed, that's the case. That's the first step of the proof. We need to prove that. I'm going to call y minus n the random variable Sn over n. Okay, so sum of the first n xi divided by n. It turns out that this is indeed a martingale for the filtration given by g minus n equals the sigma algebra generated by Sn, xn plus 1, xn plus 2, and so on. So notice that when n increases, okay, then minus n decreases, but also this sigma algebra is going to decrease. So that shows that indeed g minus n here is a filtration, okay? The smallest sigma algebra being the one when n is equal to infinity, when n goes to infinity. All right, so how do we prove that this is a reverse martingale? So the first step is to use some kind of symmetry argument and say that if you take two integers ij between 1 and n, then the conditional expectation of xi and the conditional expectation of xj given this sigma algebra are going to be equal. So why is that? Well, first, you see that those random variables, xn plus 1, xn plus 2, and so on, do not give you any information about xi and xj because of independence. Okay, that's the first thing to observe. Now, you see that if you know Sn, that gives you some information about xi and xj, but that only gives you a collection, an information about x1, x2 up to xn collectively, but not about the actual outcomes of those random variables individually. And so from that, and by using symmetry, because xi and xj are identically distributed, you can deduce that indeed xi and xj have the same conditional expectation given g minus n. All right. So then using this, now you can prove that y minus n is equal to the conditional expectation of x1 given g minus n. That shows you that this has the form of a regular martingale. Okay, we already proved that, so that's indeed a martingale indexed by negative time, so that's a reverse martingale. Okay, so how do we prove this? How do we go from here to here? Well, first, by this symmetry, I can say that for all I between 1 and n, conditional expectation of xi given g minus n is equal to this conditional expectation here. So I can just rewrite this conditional expectation in the form 1 over n times the sum for I equals 1 to n of those n terms, but they are all equal to this term, okay? So that's clear from the fact that those two quantities are equal for I and j between 1 and n. Now, next step, you want basically to use the fact that the conditional expectation is linear to inject the 1 over n times sum for I equals 1 to n inside the expected value, in which case it gives you that this quantity becomes x1 plus x2 up to xn divided by n. That's exactly this Sn over n, okay? And so you inject that inside and you get conditional expectation of the empirical mean given g minus n. Now, if you go back to the definition of g minus n, you see that it's the sigma algebra generated by a bunch of random variables, including Sn. So that means that Sn over n is measurable with respect to, for this sigma algebra. And so that tells you that you are in the case of perfect information that I explained in chapter 2. And so this conditional expectation is just equal to this random variable itself, the empirical mean. But by definition, Sn over n is just y minus n, okay? So that shows those equations. And now we have an expression of y minus n of the form conditional expectation of a fixed random variable that is integrable given your sigma algebra in your filtration. That shows that y minus n is indeed a martingale because time is negative. That's indeed a reverse martingale. So I'm writing again the details here, but I don't explain that too much. That's something we already used. You just start from your conditional expectation that you want to compute. You just replace by the definition. You use the projection rule, you get this, and then you get that. And you get that this is a martingale. We already did that a couple of times before. All right, so next step. Now that we have a reverse martingale, we want to use this theorem here, okay? So be careful, I'm just rewriting, reminding you what we proved before, but have in mind that those x minus n here have nothing to do with those xn here, okay? Now, the reverse martingale we have is not x minus n, it's y minus n. So this result tells you that y minus n, okay, which is equal to Sn over n, is going to converge almost surely, so that's good, that's what we want, to a limit that I'm going to call y negative infinity, which is equal to conditional expectation of y minus 1 given g minus infinity. G minus infinity is the intersection of all those sigma algebras here, okay? That's the limiting sigma algebra, that's a decreasing sequence, so the limit here is going to be the intersection of all those ones, okay? So that's what we can conclude here. Then because we have a reverse martingale, y minus n, which is equal to Sn over n, converges almost surely to the analog of this random variable, but I replace x by y. Now we have new notations, so that's the conditional expectation of y minus 1 given g minus infinity. Okay? Have in mind also that in the theorem we proved before, we had a conditional expectation of x0 given g minus infinity. Here I'm looking at an x minus 1, or here y minus 1, because you see that y minus n is well defined for n equals 1, but not for n equals 0. So your process starts at time 1, basically, not time 0. All right, so we get this. So we are getting closer to our result. We have that indeed the empirical mean converges almost surely to this limit. Now what we want to prove is that this limit here, this conditional expectation, is indeed equal to mu. Okay? This conditional expectation is a random variable, but we want to prove that it's almost surely constant. Okay, equal to mu, and the tool we just saw for that is this theorem that is an extension to random variables of Kolmogorov 0, 1. So remember that it says that if you have a bunch of independent random variables and you look at kind of the tail, like the sigma algebra of the tail that I call f plus, and if you have a random variable that is integrable and f plus measurable, then this random variable must be almost surely constant. That's what we want to prove for this. So, how can we do this? Well, now I have just changed of notation, but we can use, instead of f plus, I'm going to use g minus infinity. So why does it work? Well, because remember, f plus is the intersection of a bunch of sigma algebras. Here, that's the same. G minus infinity here is going to be the intersection of all those sigma algebras. Remember that to be able to apply that, we also want sigma algebras generated by independent random variables. Well, that's the case here. That's the way it's designed. Xn plus 1, Xn plus 2, and so on are independent by assumption. And Sn is the sum of the first n. But again, the first n are independent of the next ones. So all those random variables are independent, so we can use, in fact, this theorem, okay? Which says that x now is going to be this random variable, this one is almost surely constant, okay? So eventually we conclude that by Kolmogorov 0, 1 law, or I should say, to be more precise, by this theorem that is this extension of Kolmogorov 0, 1 law, we can say that the limit here, y minus infinity, is almost surely constant, so it's equal to its expected value, okay, like we saw before. Then, next step, I'm using, again, the fact that we have a limit like that. The limit is y minus infinity is conditional expectation of y minus 1 given this limiting sigma algebra, okay? And so I just replace the limit by this conditional expectation here. But then again, like basic property of the conditional expectation, the expected value of the conditional expectation is just equal to the expected value of this random variable, which I proved in chapter 2. And so we get that this is the expected value of y minus 1. But then if you go back to the definition here, y minus 1 is just s1 over 1. That's just s1. But s1 is just x1. Okay, so that's equal to the expected value of x1. Expected value of x1 is the same for all the xi. Expected value of xi in general is equal to mu. So eventually we have that indeed Sn over n, your empirical mean, which is equal to this y minus n, your reverse martingale, is going to converge almost surely to this limit, but this limit is constant, equal to mu. So indeed, that shows the strong law of large number, even when dealing with random variables that have an infinite variance. That's all for today. Thank you for watching. In the next video, I'm going to cover chapter 6 of my stochastic modeling book. This chapter is about a class of stochastic processes called Galton-Watson branching processes that are relevant in biology. Those processes can also be studied mathematically using, among other tools, martingale theory. So the next chapter is in fact another application of some of the results we saw in this video.